Located about 23 million light-years away, the Whirlpool Galaxy is a massive spiral of stars, gas and dust. Its arms contain billions of stars, regions where new stars are forming, and remnants of older stars. Visiting its centre means moving into an area with extremely high gravity, dense star clusters, and clouds of gas that produce new suns. The centre of the galaxy is full of intense activity, where gravity, light, and matter interact in complex ways. How does a galaxy function at its core? Before we dive in, let us know where in the world you're watching from in the comments below. It's always amazing to see how far our videos reach. And if you enjoy learning about space, consider subscribing. It really helps us keep making more content like this. The Whirlpool Galaxy, often called Messier 51a or NGC 5194, is one of the most beautiful and well-known spiral galaxies in the night sky. It belongs to a type of galaxy known as a grand design spiral, which means its spiral arms are clearly defined and strikingly symmetrical. At its centre lies a powerful Seyfert Type II nucleus, an active region where a supermassive black hole is surrounded by glowing clouds of gas. The Whirlpool Galaxy is found in the constellation Canis Venatici, also known as the Hunting Dogs, and it holds a special place in astronomy because it was the very first galaxy ever recognised as a spiral. This galaxy is about 31 million light-years away from Earth, which is roughly equal to about 9.5 megaparsecs. It spans an enormous width of nearly 77,000 light-years, making it a bit smaller than our own Milky Way galaxy. The Whirlpool does not exist alone in space. It has a smaller companion galaxy known as NGC 5195. The two are so close that they are physically interacting with each other. This dramatic cosmic dance between them can even be spotted through a simple pair of binoculars, which makes the Whirlpool a favourite target for amateur astronomers. Professional astronomers too have spent many years studying this pair of galaxies. By observing the Whirlpool and its companion, scientists have been able to learn more about how spiral arms form, how galaxies influence one another through gravity, and how cosmic collisions shape the universe. Because the Whirlpool and its partner are relatively nearby and so visually clear, they have become one of the most famous examples of galactic interaction ever studied. The story of its discovery goes back more than 2 centuries. On the 13th day of October in the year 1773, the French astronomer Charles Messier came across the object while searching for things that might be mistaken for comets. He added it to his famous list of fuzzy celestial objects, naming it Messier 51. Later, in the 19th century, the Irish astronomer William Parsons, the 3rd Earl of Ross, used a 72-inch reflecting telescope at Birr Castle to observe it in greater detail. What he saw astonished him. The object had a spiral shape. This was the first time anyone had ever seen such a pattern in the sky, though people at that time did not yet realise that spiral nebulae were actually entire galaxies like our own. It was only in the 20th century that the American astronomer Edwin Hubble finally proved these spiral nebulae were indeed separate galaxies far beyond the Milky Way. He did this by detecting a special kind of star called a Cepheid variable, which helped him measure their enormous distances from Earth. With the rise of radio astronomy in the mid-20th century, scientists were able to take radio images of Messier 51 and confirm beyond doubt that the Whirlpool and its companion were truly interacting galaxies. Today, when astronomers speak of Messier 51, they sometimes mean the entire system of both galaxies together. To distinguish them, the larger galaxy is called M51a and the smaller companion M51b. The Whirlpool can be found deep in the constellation Canis Venatici. Observers often locate it by starting at the bright star Alkaid, the easternmost star of the Big Dipper, and then moving about 3.5 degrees southwest. Because of its position in the sky, the Whirlpool never sets for people who live north of the 43rd parallel, meaning it can be seen year-round from northern latitudes. It is best observed from November through May, when it climbs high above the horizon during the night. Even under a dark sky, the Whirlpool can be glimpsed through ordinary binoculars as a faint patch of light. With a small telescope of about 10 centimeters in diameter, its two components become visible as distinct objects. When viewed with a telescope of 15 centimeters, the spiral pattern begins to emerge faintly. Through large telescopes of 30 centimeters or more, under truly dark skies, the galaxy's spiral arms become vivid, dotted with glowing regions of star formation. Photographs reveal far more detail than the human eye ever could. Long exposure images show faint clouds and wisps of material stretching far beyond the visible spiral arms. In 1984, using a special high-speed detector called an image photon counting system on the Canada-France-Hawaii telescope atop Mauna Kea, astronomers detected that the Whirlpool's core actually contains two distinct components, evidence of its complex and active nucleus. In January of the year 2005, the Hubble Space Telescope captured one of the most detailed portraits ever taken of the Whirlpool Galaxy. The resulting image, containing over 11,000 by nearly 8,000 pixels, revealed its sweeping arms in dazzling clarity, showing lanes of dark dust, clusters of newborn stars, and glowing clouds of gas. The Whirlpool lies between 23 and 31 million light-years from Earth. Measurements taken in 1991 suggest it is about 88% the size of our Milky Way, with a total mass of around 160 billion times that of the Sun. It is believed to be roughly 400 million years old, relatively young compared to some other galaxies. At the very heart of the Whirlpool lies a supermassive black hole. For a long time, astronomers thought this black hole was surrounded by a ring of dust. Later observations revealed that the dust actually obscures part of the black hole instead of circling it completely. From this active centre, two bright cones of ionized gas shoot outward into space, marking the galaxy's vibrant and energetic core. The Whirlpool Galaxy, often called Messier 51 or NGC 5194, is a grand and breathtaking spiral galaxy famous for its striking beauty and intricate design. It has two large and well-defined spiral arms that curl gracefully in a clockwise direction, though one of them bends slightly away from its expected path. Astronomers believe that this unusual and dramatic structure is the result of a cosmic dance between the Whirlpool Galaxy and its smaller companion, NGC 5195. According to research, this companion galaxy may have passed through the main disk of the Whirlpool Galaxy about 500 to 600 million years ago. During this ancient encounter, NGC 5195 is thought to have come from behind Messier 51, moved through its disk toward our line of sight, and then crossed it again between 50 and 100 million years ago. Today, we see it just slightly behind the Whirlpool Galaxy, locked in a slow and spectacular gravitational embrace. This close interaction between the two galaxies has created many fascinating tidal features, vast streams and plumes of stars and gas pulled out into space by their mutual gravity. The largest of these is known as the Northwest Plume, stretching an incredible 43 kiloparsecs, or about 140,000 light-years, from the galaxy's centre. This plume glows with a soft and even light, suggesting it came from the Whirlpool Galaxy itself. Nearby are two slightly bluer plumes, known as the Western Plumes, that mark more evidence of the cosmic tug-of-war between these galactic neighbours. In the year 2015, astronomers discovered two more such features, named the Northeast Plume and the South Plume. These new findings confirmed that the interaction between Messier 51 and its companion must have happened more than once. Simulations that include multiple passes of NGC 5195 through the Whirlpool Galaxy perfectly match what scientists observe today. At the heart of the Whirlpool Galaxy, stars are being born at a faster rate than usual. Astronomers say that the efficiency of this star formation, the ratio of new stars to the gas available for their creation, is around 1%, similar to that of our own Milky Way. However, this intense starburst period will not last forever. It is expected to continue for another 100 million years or so before slowing down. The spiral arms themselves also shine brightly with the young stars, glowing with the energy of new life spreading through the galaxy. Over the years, the Whirlpool Galaxy has also hosted several spectacular supernova explosions, the dramatic deaths of massive stars. The first recorded one appeared in the year 1994, known as SN 1994 the Rind, and was a Type Ike supernova caused by a massive star that had already lost much of its outer layers. Its brightness peaked at magnitude 12.91. Another explosion occurred in June 2005, when an amateur astronomer named Wolfgang Kleur discovered SN 2005 Cs, a Type II supernova that reached magnitude 14. Then, on the 31st of May in 2011, another Type II supernova, called SN 2011 DH, was observed shining with a magnitude of 12.1. It had an unusually blue spectrum and showed signs of material expanding outward at great speed, indicating that the dying star was probably a yellow supergiant rather than the more common red or blue type. On the 22nd of January in 2019, yet another fascinating event occurred. A supernova imposter, called at 2019 ABN. This was later identified as a luminous red nova, a rare kind of explosion caused when two stars merge into one. The original star that caused this event was detected in infrared images taken by the Spitzer Space Telescope, but it was hidden from view in Hubble Space Telescope photos, likely because it was buried under thick clouds of interstellar dust. Scientists studying the Whirlpool Galaxy have also discovered several types of molecules inside it. Among them are hydrogen cyanide, hydrogen isocyanide, aldehyde and diazenylium, all found throughout the galaxy's arms and core. However, certain rare molecules such as isocyanic acid and ethynyl appear only within about 1 kiloparsec of the galaxy's centre, suggesting unique chemical conditions near its heart. In September of the year 2020, astronomers using the Chandra X-ray Observatory announced the discovery of a possible planet outside our galaxy, a remarkable candidate named M51 ULS-1b. If confirmed, it would be the first known extragalactic planet. This world seems to orbit a powerful X-ray source made up of a stellar remnant, either a neutron star or a black hole, and a massive B-type supergiant star. The planet itself is thought to be slightly smaller than Saturn, and circles its host from tens of astronomical units away. NGC 5195, also known as Messier 51b, is a small dwarf galaxy locked in this ongoing cosmic interaction with the Whirlpool Galaxy. Both are located in the constellation Canis Venatici, roughly 31 million light-years from Earth. Together, they form one of the most famous and well-studied pairs of interacting galaxies in the universe. The Whirlpool Galaxy is also the brightest member of a small cluster known as the M51 group, which includes the Sunflower Galaxy, Messier 63, as well as NGC 5023 and NGC 5229. Astronomers believe this group may be part of a larger chain of galaxies that stretches out across space and could connect to the M101 group and the NGC 5866 group. A galaxy is more than just a giant gathering of stars. It is a living, breathing system filled with mysteries and invisible forces. But when astronomers look closer, the line between what makes a true galaxy and what makes a simple cluster of stars begins to blur. The deeper scientists peer into the vast universe, the harder it becomes to tell where one ends and the other begins. At its heart, a galaxy is a vast ecosystem of stars, gas, dust, and unseen energy. What truly sets it apart from a mere star cluster is the presence of an invisible but powerful ingredient: dark matter. In small star clusters, the gravity that holds everything together comes only from the stars themselves. But in galaxies, there is something extra. Dark matter, a mysterious and invisible form of mass, surrounds the galaxy like a ghostly halo. Though we cannot see it, it acts as a kind of cosmic glue, giving the galaxy strength and stability. It helps pull in gas, shapes the orbits of stars, and even shields the galaxy from being torn apart by nearby cosmic neighbours. Without this dark matter halo, a galaxy would quickly lose its structure and fall to pieces. That is why many scientists believe that the true mark of a galaxy is the presence of dark matter holding it together. The universe is full of great cosmic dances. Larger galaxies often pull on smaller ones, stretching and twisting them with enormous tidal forces. Some of these smaller systems, unable to resist the strain, are torn apart completely. Their stars are scattered like glitter across the sky. But dwarf galaxies, even the tiniest ones, often endure for billions of years because their dark matter halos act as shields, helping them survive the immense gravitational tug-of-war. This endurance is one of the reasons astronomers classify them as true galaxies, rather than mere clusters of stars. Still, not everything fits neatly into this rule. Some of the faintest galaxies ever seen, called ultra-faint dwarf galaxies, blur the line even further. These ghostly systems contain only a few thousand stars, fewer than some large clusters, but they spread their stars across a wider area and move in ways that suggest something massive and unseen is pulling the strings. That hidden force, again, is dark matter. Even though they look fragile, their invisible scaffolding makes them strong enough to be called galaxies. Another clue that separates galaxies from star clusters lies in how they give birth to stars. Galaxies are like cosmic nurseries where clouds of gas collapse to form new stars again and again, sometimes for billions of years. Star clusters, however, are born in a single burst of creation. Once their gas is used up, they can no longer make new stars. They become frozen in time, fossils of a single brilliant event. Galaxies, in contrast, keep evolving, continually recycling their gas and dust to form new generations of stars. Even the chemical fingerprints of stars tell the same story. Stars in galaxies show a wide range of elements because new stars are born from gas enriched by the ashes of older ones. In clusters, the chemistry is much simpler, locked forever in the conditions that existed when they first formed. Yet, there are exceptions. Some star clusters, like Omega Centauri and our Milky Way, display complex chemistry more typical of galaxies. Many astronomers believe that Omega Centauri might actually be the ancient core of a dwarf galaxy, stripped of its outer layers long ago. This possibility shows how fluid these categories can be, how galaxies and clusters can evolve and transform into one another over cosmic time. Astronomers can also tell the difference by studying how stars move within these systems. In star clusters, the motion of stars can be explained by the visible mass alone, but in galaxies, stars often move much faster than the visible matter can account for. Something unseen, dark matter, must be adding to the gravitational pull. By carefully tracking these motions, scientists can decide whether a faint, distant object is truly a galaxy or just a cluster of stars. Yet, even with all these signs, the debate continues. Some astronomers think that defining a galaxy strictly by the presence of dark matter is too narrow, because galaxies can lose much of their dark matter during violent interactions. Others believe that star formation is not a perfect marker either, since even galaxies can run out of gas and stop making new stars. What most agree on, however, is that galaxies are complex systems, living environments that change, grow, and sometimes die. They are not just star collections, but cosmic communities shaped by both visible and invisible forces. Drawing the line between galaxies and clusters is not simple. If the definition is too tight, we might overlook faint, ancient systems that hold secrets about how the first galaxies formed. If it is too loose, we might lose sight of what makes galaxies so special. Some of the faintest galaxies ever discovered, barely visible against the endless darkness of space, push this definition to its limits. Are these ghostly, delicate systems truly galaxies, or something entirely new, a bridge between galaxies and clusters? If the giant spiral and elliptical galaxies are like the grand rulers of the cosmos, then dwarf galaxies are their quiet, humble companions, small, faint, and easily overlooked, yet far more numerous than their majestic counterparts. They may not shine with bright spiral arms or glowing centres, but they are scattered all across the universe, filling the cosmic stage in silent abundance. In fact, when astronomers count all the galaxies that exist, most of them turn out to be dwarfs. These tiny galaxies are the lightweights of the galactic family, modest in size, dim in brightness, and sometimes so faint that they nearly vanish into the black curtain of space. To understand how small they are, consider this. Our Milky Way galaxy is home to roughly 200 to 400 billion stars. A dwarf galaxy, on the other hand, might contain only a few billion stars, or even fewer. Some of the tiniest dwarfs known hold just a few thousand stars, no more than what a single bright cluster inside our Milky Way might contain. In terms of size, a typical dwarf stretches across only a few thousand light-years, while the Milky Way spans about 100,000 light-years. Some are so compact that they could easily fit inside a single spiral arm of a large galaxy, while others are puffed up and spread thin, with their stars scattered loosely across space like faint dust in the wind. Despite their differences, these small galaxies share one defining trait. They lack the elegant structure seen in their larger relatives. Dwarfs do not have the graceful spiral arms of galaxies like Andromeda, nor do they possess the smooth, rounded brilliance of the great ellipticals. Instead, they often appear uneven and irregular, with crooked shapes and scattered patches of light. Their gas clouds look torn and ragged, as if they were unfinished creations still waiting to be moulded. This messy appearance is partly due to their weakness. Because dwarf galaxies contain far less mass, their gravitational pull is not strong enough to hold everything tightly together. As a result, close encounters with larger galaxies can easily distort them, twisting their shapes and pulling away their gas and stars. Many dwarf galaxies orbit bigger ones as satellites, and the scars of these cosmic interactions are written all over their distorted forms. Yet, these dwarfs are far from unimportant. Astronomers believe they are among the first building blocks of the universe itself. Long ago, in the early days of the cosmos, billions of years before the great spirals formed, tiny clumps of gas and dark matter gathered to create the first dwarf galaxies. Over immense stretches of time, these small systems collided and merged again and again, eventually giving birth to the massive galaxies we see today. Some dwarfs, however, managed to survive this violent era intact and still orbit their larger companions today. These survivors act like time capsules, preserving ancient clues about how galaxies first came into being. Not all dwarf galaxies look the same. Some, called Dwarf Spheroidals, are very dim and diffuse, containing only a few stars spread across a wide region. They have little or no gas, and star formation has almost completely stopped, making them ghostly and pale. Others, known as dwarf irregulars, are livelier. These contain clouds of gas and regions where new stars are still being born. In certain areas, they can glow brightly with the light of young, hot stars surrounded by shining clouds of gas. There are also dwarf ellipticals, which are smoother and rounder than irregulars, but still much smaller and less brilliant than the enormous elliptical galaxies found elsewhere in the cosmos. Compared to large galaxies, dwarfs are also poorer in heavy elements. Stars forge heavier elements through nuclear fusion and supernova explosions, but in dwarfs, these materials often escape into space. Their weaker gravity cannot hold on to the fierce blasts of exploding stars as well as larger galaxies can. Because of this, the gas in dwarf galaxies remains relatively primitive, more like the raw material of the early universe. Studying these galaxies, therefore, allows astronomers to peek back in time and understand what conditions were like before galaxies such as the Milky Way fully formed. Even though they contain far fewer stars, dwarf galaxies seem to be dominated by dark matter, the invisible substance that makes up most of the universe's mass. In fact, pound for pound, dwarfs often hold more dark matter compared to visible matter than giant galaxies do. This hidden mass helps them survive despite their faintness, acting as an unseen glue that binds them together. Because of this, scientists sometimes refer to them as dark matter laboratories, since their delicate structures make them especially sensitive to the mysterious effects of dark matter. Our own Milky Way is surrounded by dozens of dwarf galaxies. The most famous of these are the large and small Magellanic Clouds, two irregular, gas-rich galaxies visible to the naked eye in the southern sky. They are filled with young stars and glowing clouds of gas, and they are currently interacting with both each other and the Milky Way itself, twisting and pulling one another in a slow gravitational dance. Closer to home, astronomers have discovered several tiny, faint spheroidal dwarfs orbiting the Milky Way, some so diffuse that they can barely be seen, blending almost perfectly with the dark background of space. Other large galaxies also have their own dwarf companions. Andromeda, for example, is known to have more than 30 dwarf galaxies orbiting it, forming a miniature galactic system of its own. Astronomers suspect that many more remain hidden, faint and difficult to detect, waiting to be discovered with the next generation of powerful telescopes. Though small, dwarf galaxies can have a surprisingly large impact. When a giant galaxy swallows a dwarf, it can trigger bursts of new star formation, mix in fresh gas, and even reshape the structure of the larger system. The Milky Way itself bears the marks of past collisions with dwarfs, streams of ancient stars drifting through its halo like ghostly remnants of long-lost galaxies. Some of the dense star clusters we see today may even be the stripped cores of ancient dwarfs that were once devoured by our galaxy. According to advanced computer models that simulate the mysterious substance known as dark matter, galaxies like our own Milky Way should be surrounded by hundreds, perhaps even thousands, of tiny companions called dwarf galaxies. Yet, when astronomers point their telescopes to the heavens, they see far fewer than expected. This raises a puzzling question. Are these small galaxies simply too faint for us to detect? Or is there something about the way galaxies form that our theories have misunderstood? The mystery remains unsolved, but with every new dwarf galaxy discovered, we move one step closer to uncovering the truth. In the grand stage of the universe, the large, bright galaxies are like shining lighthouses blazing through the cosmic darkness, while the dwarfs are more like faint sparks scattered across the endless night. Their light is so weak and their size so small that they often go unnoticed, hidden within the background of stars and cosmic dust. To find them, astronomers must search carefully and patiently, scanning the sky with great precision. Even then, these galaxies often appear as barely visible smudges against the blackness of space. Astronomers have learned to search for these elusive companions in clever ways. One strategy is to look near larger galaxies, since dwarfs often gather around them like a family of small satellites. Around the Milky Way, for instance, the large and small Magellanic Clouds are clearly visible, but others, such as the Draco dwarf or the Ursa minor dwarf, are so dim that they can only be found through careful measurements of star brightness and motion. As telescopes have grown more powerful, astronomers have discovered more and more of these hidden companions, each new find suggesting that many more are waiting to be revealed. Another approach relies on massive digital surveys that map the sky in remarkable detail. In recent years, projects like the Sloan Digital Sky Survey have uncovered dozens of ultra-faint dwarf galaxies by detecting subtle groups of stars that move together across the sky. These discoveries have shown that the universe is filled with small galaxies, far more than we once imagined. And yet, scientists believe that what we have seen so far is only a small fraction of the whole picture. When scientists create computer simulations of how galaxies form, they begin with the invisible skeleton of the cosmos, dark matter halos. These halos are formed by the pull of dark matter, which gathers gas and creates the right conditions for stars to be born. In these models, small halos form first, and over time they merge to build larger ones. This bottom-up growth pattern naturally produces a vast number of small galaxies, far outnumbering the giants. Our own neighbourhood in space, known as the Local Group, supports this idea. It includes the Milky Way, the Andromeda Galaxy, and dozens of smaller galaxies, most of which are dwarfs. Apart from the two giant spirals, nearly all the other members are small, faint galaxies, some with irregular shapes and others with dim, spherical forms that are barely visible even through advanced instruments. This small region of space reflects a greater truth. Wherever galaxies exist, dwarf galaxies are by far the most common. A typical dwarf galaxy might contain only a few million stars, a mere handful compared to the hundreds of billions shining in a grand spiral like the Milky Way. And by the time that faint light has travelled millions of light years through space, it becomes almost impossible to detect. Astronomers must contend not only with vast distances, but also with the background glow of stars, cosmic dust, and even the light pollution from Earth itself. Many dwarfs fade into the darkness, blending seamlessly with the cosmic background. Detecting them requires extremely sensitive instruments and long hours of observation. Often, they appear not as clear, glowing galaxies, but only as small clusters of stars, bare hints of their true form. If most galaxies in the universe are indeed dwarfs, then they may hold the deepest clues to how galaxies form and evolve. Large galaxies like the Milky Way have gone through many collisions, mergers, and bursts of star formation that blur their early history. Dwarf galaxies, being smaller and simpler, preserve a clearer record of the universe's past, like ancient fossils of the cosmos. Astronomers often describe the universe as a vast cosmic web, with galaxies strung along invisible threads of dark matter and separated by immense voids. If dwarf galaxies truly dominate the numbers, then these threads, the filaments of the cosmic web, are richer and more intricate than we ever imagined. Each faint dwarf adds to the great cosmic structure, helping scientists trace the hidden framework of dark matter that binds the universe together. Without accounting for these faint galaxies, our picture of the cosmos remains incomplete. Looking toward the future, astronomers are confident that this hidden majority will soon begin to emerge from the shadows. With powerful new instruments like the Vera-C, Rubin Observatory, capable of scanning vast stretches of the sky in incredible detail, scientists expect to uncover hundreds of new dwarf galaxies orbiting the Milky Way and beyond. Space telescopes, freed from the blur of Earth's atmosphere, will peer even deeper, detecting the faintest glimmers of light that ground-based observatories cannot. As these new discoveries unfold, the quiet sparks of the universe will at last take their rightful place in the grand story of the cosmos. In the final decades of the 20th century, astronomers began using powerful computers to recreate the birth and growth of galaxies. These digital simulations were guided by the known laws of physics and by the idea that most of the universe's mass is made of dark matter, an invisible substance that outweighs everything we can see. From these experiments came a fascinating picture of what our cosmic neighborhood should look like. According to the models, galaxies like our Milky Way should not exist in isolation. Instead, they should be surrounded by hundreds, or perhaps even thousands, of much smaller companions, tiny clumps of dark matter known as halos. Many of these halos were expected to cradle miniature galaxies called dwarf galaxies. If the Milky Way were a great glowing hive, then these dwarfs would be like countless bees swarming around it. But when astronomers actually looked at the night sky, what they found was quite different. Instead of hundreds upon hundreds of these small satellites, they saw only a few dozen. This striking mismatch between what the simulations predicted and what telescopes observed became known as the missing satellites problem. The mystery was especially puzzling because the same computer models were otherwise remarkably accurate. They successfully reproduced the vast cosmic web, the enormous filaments of galaxies, the clustering of matter, and the way giant structures form over billions of years. Yet when it came to the smaller scales around galaxies like our own, the numbers simply did not add up. The dark matter halos that should exist in great numbers seemed to be there only in theory. Either they truly existed but failed to form visible galaxies, or our understanding of dark matter itself was flawed. At first, astronomers wondered if the explanation might be simple. Maybe the missing satellites were there but just too dim to detect. As technology improved, digital sky surveys began to reach fainter and fainter limits. The Sloan Digital Sky Survey, for example, revealed a host of ultra-faint dwarf galaxies scattered across the northern sky. Later on, the Dark Energy Survey uncovered even more of these faint companions in the southern sky. Each new discovery helped to narrow the gap between theory and observation, but even today only a few dozen dwarfs are known to orbit the Milky Way, still far fewer than the hundreds that models predict. If the satellites are not merely hiding, then perhaps the problem lies in the simulations themselves. Maybe the models assume too much about how gas and stars behave in tiny halos of dark matter. In theory, every dark matter halo should be able to gather gas and form stars, but in practice, many may fail. In the early universe, powerful radiation from the first stars and quasars could have blasted away gas from these small halos before they ever had a chance to grow into galaxies. Later on, when some of the first dwarf galaxies formed stars, violent supernova explosions may have blown out what little gas they had left, shutting down star formation completely. If this happened frequently, then many dark matter halos might remain truly dark, empty of stars and invisible to even the most sensitive telescopes. In this view, the missing satellites are not missing at all. They are there, but they never lit up. Another possibility is even more fundamental. Perhaps dark matter itself is not what we think it is. The standard model of cosmology assumes that dark matter is cold, meaning it moves slowly compared to the speed of light and clumps together easily. Cold, dark matter predicts the existence of many small halos, the very cause of the missing satellites problem. But what if dark matter behaves differently? If it is warm, meaning it moved faster in the early universe, it would have smoothed out the smallest structures, preventing many dwarf galaxies from forming in the first place. Or, if dark matter particles can interact with one another in subtle ways, they might erase some of those tiny halos altogether. These alternative ideas are still speculative, but the missing satellites problem remains one of the strongest reasons to explore them. The Milky Way is not the only galaxy that faces this mystery. Our neighbour, the Andromeda Galaxy, shows a similar shortage of small companions, though it seems to have slightly more than we do. Even in enormous clusters of galaxies where small galaxies are more common, astronomers still cannot find as many dwarfs as theory suggests. No matter where they look, the same puzzle appears again and again. In truth, the missing satellites problem might be two mysteries intertwined. On one hand, it could be about how galaxies form and evolve. Perhaps star formation stops more easily in small halos than scientists once thought. On the other hand, it could be about the true nature of dark matter. Perhaps this invisible material has properties we have yet to uncover. The great challenge is to tell these two possibilities apart. Astronomers hope that by finding more ultra-faint dwarf galaxies, they can prove that many small halos really do host stars. If not, then they may have to rethink what dark matter actually is. In recent years, progress has come from new techniques, such as mapping the sky for stellar streams, trails of stars that reveal where ancient satellites once orbited before being torn apart by the Milky Way's gravity. This shows that the Milky Way's current collection of dwarf galaxies is not the full story. Over the past 13 billion years, many more may have existed, only to be swallowed or destroyed. Even after accounting for this cosmic destruction, the gap between what theory predicts and what we observe remains wide. Most estimates suggest that our galaxy should have at least a few hundred satellites. Unless nearly all of them are too faint or too disrupted to detect, something deeper must be missing from our understanding. That is why astronomers call the missing satellites problem a crucial test of the standard model of cosmology. If our picture of the universe is truly correct, then those hidden satellites must be out there, waiting to be found. Whether the answer lies in faint galaxies we have not yet seen, in new physics we do not yet understand, or in some blend of both, this enduring puzzle continues to push science forward, urging us to look deeper into the shadows of our cosmic home. In the early days of astronomy, finding a dwarf galaxy often happened purely by chance. A patient astronomer, spending long hours examining photographic plates of the night sky, might notice a tiny, faint blur that didn't look quite like a star cluster. These early discoveries were uncertain and confusing because it was hard to tell whether such faint patches were true galaxies or just loose groups of stars drifting together in space. But as technology advanced and film photography gave way to digital imaging, everything began to change. Astronomers started creating surveys designed specifically to hunt for these faint, ghost-like smudges. Wide-field surveys became one of their most powerful tools. They allowed scientists to map enormous portions of the sky in remarkable detail, capturing even the dimmest and most delicate traces of light. One of the greatest breakthroughs came with the Sloan Digital Sky Survey, or SDSS. Using a special telescope located in the US state of New Mexico, the SDSS scanned huge stretches of the sky with extraordinary accuracy. It produced one of the most complete and detailed maps of stars and galaxies ever made. Within this immense collection of data, astronomers began to notice tiny patches, small regions where there seemed to be more stars than expected. These regions, called overdensities, often turned out to be dwarf galaxies hiding in plain sight. What was once invisible to the human eye could now be detected through the power of data and careful statistical analysis. Instead of looking directly for a glowing spot in the night sky, scientists began searching for subtle increases in star counts. A dwarf galaxy might not appear as a shining cloud, but rather as a small bump on a graph showing how many stars were present in a particular area. Those small bumps, barely noticeable at first, became the fingerprints of unseen galactic companions. This method proved especially effective when studying the area around our own Milky Way galaxy. The Milky Way contains billions of stars, making the sky crowded and confusing. Yet, within this chaos, a dwarf galaxy can sometimes be recognized by the shared traits of its stars. They might all be older, dimmer, or redder than typical Milky Way stars. By carefully filtering the data for these specific types of stars, astronomers can separate the faint whisper of a dwarf galaxy from the overwhelming brightness of the Milky Way. Some of the faintest and smallest galaxies discovered in the past 20 years are so dim that they challenge the very definition of what a galaxy is. These ultra-faint dwarfs contain so few stars that, if you were standing inside one, you might not even realize it. The stars would be so far apart that the night sky would look nearly the same as it does from Earth. To detect such fragile systems, astronomers now rely on incredibly deep and sensitive sky surveys. One of the most successful of these has been the Dark Energy Survey, which used a telescope with a mirror about 4 meters wide in Chile. By capturing images of the southern sky in great depth, it uncovered dozens of ultra-faint dwarf galaxies orbiting the Milky Way. Modern instruments also allow astronomers to confirm whether a group of stars is truly a galaxy by studying motion. A random cluster of stars might look like a galaxy, but its stars move independently. In a real galaxy, however, all the stars move together, held in place by a shared gravitational pull. Using highly sensitive spectrographs, astronomers can measure tiny shifts in starlight that reveal whether the stars are bound together. If they are, it means there is hidden dark matter, an invisible glue that makes the system a true galaxy. The Hubble Space Telescope has played a vital role in this process. Floating above Earth's atmosphere, it can see individual stars inside suspected dwarf galaxies with crystal clarity. By studying these stars, astronomers can determine their ages and confirm whether they belong to a genuine galaxy or not. And the search is far from over. Future telescopes promise to take this quest even further. The upcoming Legacy Survey of Space and Time will scan the sky repeatedly, creating a dynamic and ever-changing map of the universe. It will not only reveal new faint galaxies, but also show how these hidden worlds evolve with time. The search for dwarf galaxies is slow, careful, and ongoing, like listening for faint echoes in a vast cosmic hall. But with each new discovery, with every tiny smudge of light identified, our understanding of the hidden structure of the universe grows a little clearer and more wondrous. All around the Milky Way, like bees circling a great hive, dozens of smaller companion galaxies move in silent orbits. These little galaxies, known as satellites, come in many different shapes, sizes and styles. Some are bright and full of energy, while others are dim and ghost-like. Yet, together, they form a fascinating and diverse family that tells the story of how galaxies live, grow, and change through time. The most famous of these companions are the two Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. These two are so bright that people in the southern hemisphere can see them without a telescope, glowing like pale smudges against the night sky. The Large Magellanic Cloud, often called the LMC, is by far the biggest of the Milky Way's companions. It contains roughly 30 billion stars, making it a small galaxy in its own right. Its smaller sibling, the Small Magellanic Cloud, or SMC, holds only a few billion stars, yet it still shines more brightly than nearly all the other dwarf galaxies nearby. Neither of these clouds looks like the grand spirals or smooth ovals of the great galaxies. They are irregular in shape, more like cosmic clouds torn by invisible winds. Both are rich in gas, glowing with regions where new stars are being born. Inside them lie vast stellar nurseries, where clusters of young stars light up the surrounding gas in colourful nebulae. Because of their closeness to the Milky Way and their constant gravitational dance with it, and with each other, the Magellanic Clouds have become two of the most studied galaxies in the sky. Beyond these heavyweights lies a crowd of smaller, fainter galaxies, the Dwarf Spheroidals. These are so dim that for centuries they escaped human notice. They contain only a few 100,000 stars, spread thinly over large regions of space, giving them a ghostly, almost transparent appearance. Unlike the Magellanic Clouds, these dwarfs hold little or no gas, and they are not forming new stars anymore. They're quiet and ancient, filled only with old, fading suns. Examples include the Sculptor, Fornax and Carina dwarfs, each one a dim gathering of aged stars orbiting tens to hundreds of thousands of light-years from the Milky Way's heart. Some satellites lie even closer, drifting quietly through the Milky Way's halo. The Sagittarius dwarf galaxy, discovered in the 1990s, is one such example. It is being slowly torn apart as it plunges through the Milky Way's disk. Its shattered remains form long stellar streams that curve gracefully across the heavens, a trail of stars marking the path of a galaxy being devoured. The Canis Major dwarf, another small companion, is meeting a similar fate. Its stars are stretched into great arcs that wrap around the Milky Way's outer edges like ghostly ribbons. These fragile systems remind astronomers that a galaxy's boundaries are never sharp or fixed. Stars can be stolen, gas can be stripped away, and once separate galaxies can merge into one. When astronomers map out the Milky Way's satellites, they find that this great family stretches hundreds of thousands of light-years from the galactic centre. Some companions, such as Leo-M and Leo-Tsud, orbit far away, almost 1 million light-years from the Milky Way, near the outermost limits of its gravitational reach, where its pull begins to compete with that of the Andromeda Galaxy. Even so, these distant dwarfs remain loyal to the Milky Way's gravity, tracing slow, graceful orbits that take billions of years to complete. Each one adds a unique story to the Milky Way's history, some showing traces of ancient starbursts, others made only of old stars left from a long, quiet past. Astronomers classify these companions in many ways. The gas-rich irregulars like the Magellanic Clouds are bright and rare, their beauty catching the eye. The gas-poor spheroidals are far more common but faint, scattered widely through the galactic halo. The ultra-faint dwarfs, some containing only hundreds or thousands of stars, stretch the very definition of what a galaxy can be. Together, they form a continuous spectrum, from mighty clouds blazing with starbirth to dim relics barely glowing in the dark. Distance adds yet another layer to this picture. A few dwarfs lie very close, just tens of thousands of light-years away, while others drift so far that the Milky Way's pull weakens and Andromeda's begins. The satellites are not evenly spread out. Instead, they gather in clumps or appear in long streams, which may be the remnants of larger galaxies that broke apart long ago. Some astronomers even suggest that the satellites form vast planes or patterns, though whether this is a real structure or only an illusion of perspective is still uncertain. The Magellanic Clouds, each with billions of stars, represent the giants of this family. The spheroidals, with millions, form the middle class, while the ultra-faints, with only hundreds or thousands, are the tiny fossils of the earliest cosmic times. Yet all of them, no matter how big or small, are recognized as galaxies. By studying this grand neighborhood, astronomers are not only learning what exists now, but also reconstructing the long story of galactic evolution. The bright irregulars may be newcomers, recently captured by the Milky Way's gravity. The faint spheroidals may be ancient survivors, stripped and battered by tidal forces over billions of years. And the ultra-faint dwarfs may be the oldest fossils of all, the miniature remains of the very first galaxies that ever formed in the universe. Each companion, whether bright or faint, tells a different part of the Milky Way's tale. Together, they form a living, ever-changing portrait of how galaxies grow, interact, and endure across the endless ages of cosmic time. If we could somehow remove the bright glow of the Milky Way's main disk and look only at the vast halo surrounding it, the view would be far from empty. Instead of smooth darkness, we would see something that looks like a spider's web made of starlight, thin, delicate strands stretching across unimaginable distances. These glowing threads are known as stellar streams. They are not complete galaxies anymore. Each one is a ghostly remnant, the shredded remains of a smaller system whose stars were pulled apart and scattered by the Milky Way's immense gravity. The halo of our galaxy is full of these streams, like a cosmic graveyard of smaller companions that once orbited proudly, but could not resist the pull of the giant at the centre. Imagine a small galaxy wandering too close to the Milky Way. At first, its stars stay together, bound by their own mutual gravity. But as it circles the larger galaxy, the Milky Way's powerful tidal forces begin to stretch it apart. The stars on the far side feel a slightly weaker pull, while those on the near side are tugged harder. Slowly, over millions of years, the little galaxy starts to unravel. Its stars peel away, forming two long tails that trace its orbit, wrapping around the Milky Way like ribbons of light that can stretch for hundreds of thousands of light years. What was once a single, compact galaxy becomes a thin, shimmering stream of stars, almost impossible to separate from the rest of the halo, except through careful study. One of the most famous examples of this process is the Sagittarius Stream, the scattered remains of the Sagittarius dwarf galaxy. Its stars form graceful arcs that nearly encircle the entire Milky Way. Other beautiful examples include GD1, the Orphan Stream, and Palomar 5. Some of these were born from disrupted dwarf galaxies, while others came from globular clusters, tight balls of stars that were slowly torn apart. Each stellar stream is like a fossil, preserving the memory of what once was. By studying their positions and motions, astronomers can trace the orbits of long-vanished systems and piece together the Milky Way's growth over billions of years. Detecting these streams, however, is not easy. Most are incredibly faint, nearly lost among the countless background stars. But thanks to modern sky surveys that map the heavens in great detail, more and more of these delicate structures are being discovered. What once seemed invisible now appears as clear, measurable patterns sweeping across the sky. Yet these streams tell us more than just stories of destruction. They also reveal secrets about dark matter, the mysterious substance that makes up most of the galaxy's mass. If the Milky Way's dark matter halo were perfectly smooth, the streams would form elegant, unbroken lines. But many appear clumpy or twisted, as if disturbed by invisible hands. These distortions may be caused by dense lumps of dark matter, small halos that never became galaxies themselves. In this way, stellar streams act like natural detectors, allowing scientists to map the hidden structure of the Milky Way's dark matter. Even after a dwarf galaxy is completely absorbed, its stars do not disappear. They continue to move together for billions of years, slowly spreading out and blending into the halo until their stream fades beyond recognition. Before they vanish completely, however, they offer a precious glimpse into the galaxy's violent past. Some astronomers describe the Milky Way's halo as a vast archive, and each stellar stream as a document recording one chapter of its formation. Without these streams, much of the galaxy's history would remain hidden. The Orphan Stream is one of the most haunting examples. Its name is fitting, because the parent galaxy that created it has been destroyed so completely that only its glowing trail remains. By studying the motion of its stars, astronomers can reconstruct the orbit of the lost system, but the original dwarf galaxy itself is gone forever. Palomar 5 tells a slightly different story. It still has a surviving heart, a globular cluster at its centre, but it is slowly dissolving, shedding stars into two long tails that stretch far into space. Observations show that, in time, even this surviving core will disappear, leaving behind only a stream of stars as a memory of what once was. Some streams are twisted, folded or tangled, shaped by multiple encounters over countless orbits. Each passage around the Milky Way pulls away more stars, creating overlapping arcs that at first look chaotic. But when astronomers study them carefully, they find patterns, echoes of repeated destruction and renewal. These patterns help scientists test their theories about how the Milky Way grew, layer by layer, through the slow absorption of smaller companions. In a deeper sense, stellar streams are symbols of continuity. The dwarf galaxies and star clusters that once created them no longer exist in their original forms, but their stars still shine, now part of a much greater whole. The Milky Way's brightness and grandeur are in part built from these ancient sacrifices. Without them, our galaxy would be smaller, dimmer, and far less magnificent. The Large Magellanic Cloud, often called the LMC, is far more than a simple companion following the Milky Way. With its wide sweep of stars, glowing regions where new suns are being born, and spiral-like patterns curling through its disk, it looks like a small but complete spiral galaxy, a miniature version of the grand spirals scattered across the cosmos. To anyone standing in the southern half of Earth, it appears in the night sky as a faint misty cloud, visible even without a telescope. People noticed it long before anyone dreamed of building one, and it has been a familiar sight to travellers, sailors, and storytellers for thousands of years. What makes the LMC so special is its brightness and structure. Among all the Milky Way's companions, it is by far one of the most striking and one of the most studied. Its total mass in stars is about 1/10 that of the Milky Way, a huge amount for a satellite galaxy. Hidden within it is a vast halo of invisible dark matter, an unseen force that holds it together even when it swings dangerously close to our own galaxy's gravitational pull. This invisible glue has kept the LMC from being torn apart, preserving its shape and order. When astronomers look closely, they can see how the stars of the LMC are arranged in clear, graceful patterns, spiral arms winding outward from a bright bar-shaped core of stars, just like in galaxies much larger than itself. That is why the LMC holds such a strange position among galaxies. It seems to stand halfway between being an independent spiral and being a smaller follower bound to the Milky Way. Inside the LMC, stars are forming at a furious pace. Compared with many nearby galaxies, including our own, the rate of new star birth is astonishingly high. At the heart of this activity lies one of the brightest and most famous stellar nurseries in the entire sky, the Tarantula Nebula. This immense cloud of glowing gas and dust stretches for hundreds of light years, and inside it, new stars are being born in great swarms. Some of the most massive and luminous stars ever discovered blaze there, shining so fiercely that they light up the entire nebula. Astronomers have also watched supernovae, the deaths of stars, erupt within the LMC, their explosions briefly outshining entire galaxies. In the year 1987, a supernova exploded inside the LMC. It was the closest such event seen from Earth in modern times, and offered astronomers an unmatched opportunity to watch, almost in real time, how a star dies and transforms its surroundings. The explosion, named Supernova 1987A, remains one of the most significant astronomical events of the past century, and it took place right inside this remarkable neighbouring galaxy. Unlike many smaller galaxies that have lost most of their gas, the LMC still holds rich supplies of hydrogen, the raw fuel for creating new stars. This abundance may come from its relatively large size or from the path of its orbit, which seems to have only recently brought it near the Milky Way. Some studies suggest that the LMC is making its first close approach to our galaxy and has not yet completed even a single orbit around it. If that is true, we are witnessing the LMC at a special moment in time, just as it begins to feel the powerful pull of its giant neighbour. For many years, astronomers believed the LMC had been circling the Milky Way for billions of years, but newer, more precise measurements of its motion show that it might be moving too fast for that to be possible. Instead, it could be a newcomer, a once independent galaxy that has only recently entered the Milky Way's gravitational territory, possibly bringing along its own tiny companions. If that is the case, then the LMC is not an ancient partner, but a bold visitor now being drawn into a new relationship. The pull between the LMC and the Milky Way is not one-sided. The LMC's own gravity is strong enough to tug at our galaxy, slightly altering the movement of stars within the Milky Way's disk. Some astronomers even think the dark matter halo surrounding the Milky Way may be warped by the LMC's attraction. The two galaxies are linked not only by gravity but also by a long ribbon of gas called the Magellanic Stream, a vast trail stretching across the sky, stripped from both the LMC and its smaller companion by powerful tidal forces. One day, that stream may fall into the Milky Way itself, feeding it with fresh gas and sparking new waves of star formation. If the Milky Way were smaller or the LMC more distant, we might not call it a satellite at all. It exists in a grey area, blurring the line between the categories astronomers like to draw. Nature, as always, refuses to be neatly labelled. Galaxies, like people, come in many forms, often defying simple classification. For humans, the Large Magellanic Cloud has always been more than an object of study. It has been a source of wonder. Long before telescopes or space probes, sailors and storytellers in the southern hemisphere wove it into their legends and their maps of the heavens. Today, with modern instruments, we can peer deep into its heart, counting its stars and tracing its history. Yet even now, the LMC remains both familiar and mysterious, near enough to touch with our telescopes, but distant enough to remind us how vast the universe truly is. Close by drifts its smaller sibling, the Small Magellanic Cloud, or SMC, a far more chaotic companion. Unlike its larger neighbour, it lacks the elegant spirals or smooth glow of an ordered galaxy. Instead, it appears uneven and lopsided, a scattered patch of light rather than a neatly built structure. The reason lies in its situation. The SMC lives in constant tension, caught in a gravitational tug-of-war between two giants, the LMC and the Milky Way. Its strange shape is a direct result of being pulled in different directions at once. The SMC is about 200,000 light-years away from Earth, making it one of the closest galaxies beyond the Milky Way. It contains only a few 100 million stars, a tiny population compared to the LMC or our own galaxy, so by any measure, it is a small galaxy even among dwarfs. But its closeness gives astronomers an extraordinary chance to watch it change. They can see how its stars move, how its gas is stretched and twisted, and how its very shape shifts over time. Instead of a smooth sphere or a clear disk, the SMC looks like a tangled pattern of dense star clusters and empty gaps. One section forms a compact main body, while another seems to trail away like a wing being pulled from a bird in flight. This distorted form is the direct result of tidal forces, gravity's long, invisible fingers pulling it apart. The two Magellanic Clouds are so near each other that they travel together through space, orbiting the Milky Way as a pair, bound by the same cosmic dance that has linked them for billions of years. For billions upon billions of years, the two Magellanic Clouds have likely been circling each other in a slow, graceful dance, while at the same time inching ever closer to our own Milky Way galaxy. Their shared gravity keeps them bound together, like two partners locked in a cosmic embrace, but that same force also twists and stretches them in remarkable ways. The Small Magellanic Cloud, often called the SMC, is the lighter of the pair, and because of that, it bears the most visible scars from their constant gravitational tug-of-war. Astronomers believe that the strange wing-like extension of the SMC is the result of a dramatic close encounter with its larger companion, the Large Magellanic Cloud, or LMC. During that meeting, the stronger LMC pulled away a portion of the SMC's material, leaving behind a long trailing stream that stretches far into space. This isn't the only clue to the SMC's turbulent life. When scientists study the two clouds using radio telescopes, they discover something astonishing, a vast river of gas that seems to flow out of them, arching across the heavens for hundreds of thousands of light years. This enormous structure, known as the Magellanic Stream, is believed to have formed as the two galaxies repeatedly tugged at each other. Much of its precious gas has been stripped away, leaving it looking uneven and patchy. This loss of gas also affects how new stars are born within it. Normally galaxies form stars from dense, cold clouds of gas, but in the SMC, astronomers have found signs that its star-making process has been anything but steady. Some regions burst with clusters of dazzling young stars, evidence that gravitational pressure from past encounters has triggered sudden waves of star formation. Other areas, by contrast, seem almost barren, as if the raw material for making stars has already been swept away. This uneven pattern tells the story of a galaxy caught in a constant struggle for survival. Because the SMC lies relatively close to us, scientists can study it in great detail. Modern telescopes and instruments can even track the movement of individual stars within it, measuring how they drift through space. These observations reveal that the SMC isn't peacefully orbiting the Milky Way at all. It follows a tangled, changing path, shaped by powerful gravitational forces. Its irregular, stretched-out form may be a sign that it is still adjusting to the Milky Way's pull, its structure reshaped with each passing age. Astronomers still debate what the future holds for these two companion galaxies. Some believe that the SMC and LMC will eventually merge, forming a single larger dwarf galaxy, though still far smaller than the Milky Way itself. Others think that the Milky Way's immense gravity will tear them apart first, scattering their stars like glowing breadcrumbs across the sky, forming faint stellar streams that will one day mix with our own galaxy's halo. Whatever the outcome, the small Magellanic Cloud is already changing before our eyes. Its fuzzy, mist-like glow can still be seen with the naked eye from the southern hemisphere on clear, dark nights. Long before telescopes existed, sailors used it as a guide on their journeys across the oceans, noting its strange, hazy light in the night sky. Only centuries later did scientists realize that this cloud was not a cloud at all, but an entire galaxy, a small and fragile world being reshaped by the invisible hands of gravity. The SMC stands as a vivid reminder of what happens when small galaxies live in the shadow of giants, forever pulled, stretched, and transformed by forces they can never escape. The Magellanic Bridge is like a shining rope of stars and gas that links the large and small Magellanic Clouds together, almost as if the two galaxies were holding hands across the vast emptiness of space. For a long time, astronomers believed these two clouds were just separate neighbours drifting near the Milky Way. But in the 20th century, new observations revealed something far more intimate. The two are actually bound by gravity, and their mutual pull has drawn gas and stars out of the small Magellanic Cloud, stretching them into the space between. When scientists looked closer, they discovered something truly beautiful. Streams of bright young blue stars shining across this cosmic bridge. These stars were not ancient leftovers but newly born suns, formed when the torn gas was squeezed and heated during its journey between the two galaxies. In other words, the bridge is not just a connection, it is alive with creation, a place where galaxies meet, collide, and give birth to new stars. The Magellanic Bridge is a frozen moment in time, a snapshot of motion and transformation. It captures material that is being pulled, exchanged, and reshaped as the two galaxies continue their slow, gravitational dance. But beyond this bridge lies something even grander, the Magellanic Stream. Unlike the bridge that lies between the clouds, the stream trails far behind them, winding across the southern sky like a ghostly ribbon or the glowing tail of a comet. This enormous stream is made mostly of hydrogen gas and stretches over more than 600,000 light-years, longer than the Milky Way itself. It is so faint that no human eye can see it, yet radio telescopes tuned to the special frequency of neutral hydrogen can trace it clearly. What the stream reveals is the story of countless close encounters between the Magellanic Clouds and our own galaxy. Each time they sweep near the Milky Way, powerful tidal forces tug at them, pulling loose great swaths of gas that trail behind in space. Over billions of years, these encounters have woven a vast ribbon of material that circles much of the southern sky. Gas is the lifeblood of galaxies. It is the raw material from which new stars are born. When a galaxy loses too much of it, star formation slows down and the galaxy begins to fade into quietness. The Magellanic Stream tells us that the clouds are gradually losing their precious gas and cannot hold on to it forever. One day, much of this material will drift into the Milky Way, feeding its outer halo and perhaps sparking new generations of stars in our own galaxy. But the bridge and stream are not smooth or uniform. They are filled with knots, clumps and filaments, signs of chaotic, uneven forces at play. Some regions glow with dense gas, while others fade into near invisibility. Astronomers believe this irregular pattern is caused by several things. Part of it comes from the uneven gravity of the Milky Way, which tugs harder on some areas of the clouds than others. Another part may be due to the interaction between the stripped gas and the thin, scorching halo of plasma that surrounds our galaxy, a region called the Circumgalactic Medium. As the Magellanic gas drifts through this hot halo, it is twisted, stretched, and even eroded, leaving behind a tangled and frayed pattern instead of a neat, smooth arc. In distant galaxies across the universe, astronomers often witness similar scenes, galaxies merging, colliding, or tearing each other apart. Yet those distant events are so far away that we can see only their rough outlines. Here, in our own cosmic neighbourhood, we can study these processes up close, mapping the gas almost cloud by cloud and star by star. The Magellanic Bridge shows what happens when two small galaxies come close enough to share and exchange matter, while the Magellanic Stream reveals what happens when those same galaxies are drawn into the gravitational grip of a much larger one. Together, they act as a natural laboratory of cosmic physics, a place where we can see the slow, graceful power of gravity shaping galaxies over millions of years. Thanks to modern instruments such as the Australia Telescope Compact Array, the Parkes Radio Telescope, and space observatories like Gaia, astronomers are now uncovering the finer details of this intergalactic story. By carefully tracking how the stars in the bridge move, they can reconstruct the moment when the two clouds last came closest together. By studying the chemical makeup of the stream, they can tell whether most of the gas came from the small Magellanic Cloud, the large, or a mix of both. The Sagittarius Dwarf Galaxy is a fragile little world caught in the mighty grip of the Milky Way's overwhelming gravity. Unlike the Magellanic Clouds, which still hold themselves together, Sagittarius is already being ripped apart piece by piece. It is a vivid, living example of what astronomers call galactic cannibalism, the slow devouring of one galaxy by another. Astronomers first noticed the Sagittarius dwarf in the early 1990s, but even then, it was already showing clear signs of destruction. Its stars were not neatly packed together as in many other dwarf galaxies. Instead, they had been stretched out into faint, ghostly streams that looped all the way around the Milky Way, like the scattered beads of a broken necklace glimmering faintly across the heavens. The galaxy was no longer a tight, round cluster, but a long, shredded ribbon of stars, slowly being torn apart by forces that had been at work for billions of years. The fact that it was discovered so recently shows just how dim and faint it had become after losing much of its original brightness and mass. Much of what once belonged to Sagittarius now drifts freely within the Milky Way's vast halo, stolen away by the stronger galaxy's gravity. The story of Sagittarius begins with its dangerous orbit. Unlike a quiet companion that keeps a safe distance, this small galaxy plunges straight through the Milky Way's disk, ensuring violent encounters every time it passes. Each passage exposes it to powerful tidal forces. The Milky Way's immense gravity pulls harder on Sagittarius's near side than on its far side, slowly prying away its stars and gas. With every orbit, more of its material is stripped away, layer after layer, until only a small, faint core remains. This ongoing destruction leaves scars that stretch across the night sky. The stars that once belonged to Sagittarius now form long, graceful streams that wind around the Milky Way like a silvery ribbon wrapped around a globe. These streams are not only beautiful, they are also deeply valuable to science. They act like cosmic breadcrumbs, marking the invisible shape of the Milky Way's gravitational field. By tracking the paths of these scattered stars, astronomers can map the hidden structure of our galaxy and even estimate where the mysterious dark matter, the invisible substance that makes up most of the Milky Way's mass, is concentrated. In this way, the slow death of the Sagittarius dwarf has become an unexpected gift. It helps astronomers study how our galaxy works from the inside out. Some researchers even believe that each time Sagittarius has plunged through the Milky Way, it has caused bursts of new star formation. As it passed through, it may have stirred up enormous clouds of gas, squeezing and compressing them until they collapse to form fresh generations of stars. If that is true, then the legacy of Sagittarius is not just in the stars it lost, but also in the stars it helped create, new suns that now shine proudly within the Milky Way itself. The relationship between the two galaxies is both destructive and creative, parasitic yet productive. Sagittarius is not the first dwarf galaxy to be devoured, and it will certainly not be the last. The Milky Way's vast halo is sprinkled with the remains of many past meals, faint star streams that once belonged to other small galaxies or ancient clusters. Each of these glowing trails tells the story of a long-ago encounter and a smaller companion that was torn apart. But Sagittarius stands out among them all because its demise is happening right now, before our eyes. It is a rare chance for astronomers to witness the drama of galactic cannibalism in action. Today, what remains of the Sagittarius dwarf is just a pale, fading core orbiting about 70,000 light-years from the Milky Way centre. It still barely counts as a galaxy, but only just. Compared to the grand, rounded form it must once have had, it is now a ghostly shadow of itself. Its stars have been scattered across the sky, blending with those of the Milky Way so completely that many are now impossible to tell apart. Over time, its remaining core will continue to shrink until even that is gone, fully absorbed by the much larger galaxy that has consumed it. This raises deep questions. How many of the Milky Way's countless stars were actually stolen from smaller galaxies rather than born within it? How many ancient dwarfs were swallowed long before we could ever detect their traces? And how much of our galaxy's current shape and richness comes from this long history of cosmic feasting? In the tragic yet magnificent story of Sagittarius, we see one clear answer. It shows us in real time how galaxies grow. They merge, blend, and consume one another until their individual histories become one shared tale. One day, far in the future, the Milky Way itself will collide and merge with the Andromeda Galaxy in an event of unimaginable scale. But the same fundamental process will be at work, the same gravitational hunger that now devours Sagittarius. The faint streams of stars stretching from this little galaxy are, in truth, the first glimmers of that grand and inevitable cosmic dance. The Fornax Dwarf Spheroidal Galaxy is a quiet and rather modest companion of the Milky Way. It drifts peacefully through space about 460,000 light-years away, shining faintly in the southern constellation known as Fornax. At first glance, it doesn't look like much, just a dim, hazy patch that can easily disappear into the deep black of the night sky. But hidden within this small, unassuming galaxy is a remarkable secret that sets it apart from all others of its kind. Fornax is home to not one, not two, but at least 6 globular clusters, dense, ancient gatherings of stars that usually belong to much larger galaxies. For such a faint and fragile galaxy, this is nothing short of extraordinary. The fact that Fornax holds so many of these star clusters has puzzled astronomers for decades. It raises fascinating questions about how such a small galaxy could have formed, survived, and even thrived in the shadow of a giant like the Milky Way. Globular clusters are among the oldest structures in the universe. Each one is like a glittering ball made up of hundreds of thousands of stars bound tightly together by gravity, and many of them are more than 10 billion years old, nearly as old as the universe itself. In the Milky Way, there are more than 150 of these clusters, scattered through its vast halo. Their age and structure tell a story of endurance, showing that they were formed during the earliest ages of the cosmos, when galaxies were still young and chaotic. That is why Fornax's 6 globular clusters are such a surprise. Dwarf spheroidal galaxies are usually too small and too light to hold onto such massive star systems. They lack the strong gravity and dense gas clouds needed to create or sustain them. Yet Fornax, with only a few billion times the mass of our Sun, has managed to keep 6 of them in orbit, a number that rivals even some mid-sized galaxies. These clusters are scattered at different distances around Fornax, shining faintly like tiny jewels around a dim lantern. Some stay close to the galaxy's heart, while others drift far enough that they seem to balance on the edge of escape. Astronomers have studied them closely, for the stars inside these clusters are like fossils, preserving clues about what the early universe was like. Many of the stars are older than 10 billion years, meaning they formed when the cosmos was still in its youth. Their existence suggests that Fornax, though faint today, may once have been much richer, filled with gas and alive with bursts of star formation. Unlike the Sagittarius dwarf galaxy, which is currently being torn apart by the Milky Way's powerful gravity, Fornax appears to be stable and peaceful. Its stars are not being stripped away, and its clusters remain in orbit safe and secure. This stability suggests that Fornax moves in a distant, gentle path around our galaxy, far enough to avoid being pulled apart by its enormous gravitational tides. At nearly 500,000 light-years away, it circles the Milky Way at a comfortable distance, where the cosmic forces are weaker, allowing it to preserve its delicate shape. Yet one great mystery remains. Why does Fornax have so many globular clusters? Astronomers have proposed several ideas. One possibility is that Fornax was once much more massive than it is today. Perhaps it began its life with a deep pool of dark matter and abundant gas, forming many clusters in its youth. Over time, it may have lost much of its outer layers through encounters with other galaxies, leaving only its inner core and its ancient clusters behind. Another idea is that Fornax captured some of its clusters from nearby dwarf galaxies. In the crowded outskirts of the Milky Way, galaxies sometimes brush past one another, swapping stars and clusters like cosmic traders. Maybe Fornax was simply lucky, in the right place at the right time to gather more than its share. The presence of these clusters also reveals something about the invisible structure surrounding Fornax, its dark matter halo. To keep the clusters in stable orbit for billions of years, Fornax must have a deep and steady gravitational field. If it contained only the stars we can see, the clusters would have drifted away long ago. Their survival is strong evidence that Fornax is wrapped in a vast unseen sphere of dark matter, holding everything together. Astronomers have noticed another curious detail. The globular clusters of Fornax don't perfectly match the stars in the galaxy's main body. The clusters are older and poorer in heavy elements, meaning their stars contain fewer metals than the ones in Fornax's core. This suggests that the galaxy experienced more than one wave of star formation, an early intense period that created the ancient clusters, followed by a slower, later phase that gave rise to younger stars near its centre. The clusters, therefore, are survivors from the first chapter of Fornax's story, while the rest of the galaxy shows how it evolved afterward. Because of its unusual richness and calm nature, Fornax has become a favourite target for astronomers, using both ground-based telescopes and space observatories. Deep photographs of the galaxy reveal layers upon layers of stars, from the oldest red giants to those born only a few billion years ago. Unlike some dwarf galaxies that seem frozen in time, Fornax has continued to form stars long after its birth, though never with the furious activity of a grand spiral like the Milky Way. This extended history may explain why it still holds its many clusters, a legacy of steady, patient evolution rather than violent change. The contrast between Fornax and Sagittarius shows just how different dwarf galaxies can be. Sagittarius, once bright and grand, is now being torn apart, leaving trails of stars stretched across the heavens. Fornax, more distant and tranquil, has endured, a survivor keeping its ancient treasures safe. Its globular clusters are like relics in a cosmic museum, reminders of a long-lost era when the galaxy was vibrant with new stars. Fornax may not be as massive as the Great Magellanic Clouds, but neither is it as fragile as the tiniest ultra-faint dwarfs that barely cling to existence. Its story is one of balance, quiet endurance and hidden richness. And above all, its wealth of globular clusters challenges astronomers to rethink how small galaxies can grow, evolve, and preserve the shining memories of their youth across the endless ages of the universe. The Sculptor and Sextans dwarf galaxies are two quiet, unassuming companions of the Milky Way, orbiting it at gentle, moderate distances. Unlike the restless and dramatic galaxies that are being torn apart or reshaped by gravity, these two seem content to live slowly, changing little over the course of billions of years. They show us a calmer side of galactic life, one of quiet endurance and long survival. The Sculptor dwarf galaxy lies about 290,000 light-years away from Earth, on the far edges of the Milky Way's gravitational influence. It was discovered in the year 1937 by the astronomer Harlow Shapley, who noticed a small clustering of dim stars in the southern constellation known as Sculptor. Even today, the galaxy is so faint that it can only be seen through telescopes, and even then, it easily blends in with the foreground stars of our own galaxy. To the naked eye, it appears merely as a faint smear of light against the darkness, a ghostly glimmer in the cosmic sea. But behind that faint light lies a spheroidal galaxy containing only a few million stars. Most of these stars are ancient, and there is very little sign that any new ones have formed in a very long time. Unlike the bright and lively Large Magellanic Cloud, which is still actively giving birth to new stars, the Sculptor galaxy seems to have stopped that process billions of years ago. Its supply of gas, the raw material from which stars are born, has either been stripped away by the Milky Way's gravity or used up entirely, leaving only the aging stars behind. These stars are metal poor, meaning they contain very few elements heavier than hydrogen and helium. That tells astronomers that Sculptor formed its stars very early in the universe's history, before repeated generations of supernova explosions could enrich the surrounding gas with heavier elements. The Sextans dwarf galaxy, discovered much later in the year 1990, is even fainter and more elusive than Sculptor. It lies around 320,000 light-years from Earth, in the direction of the constellation Sextans. It is one of the dimmest galaxies ever found, so faint that even the best telescopes barely pick it out from the blackness of space. To detect it, astronomers had to carefully count faint stars one by one, since the galaxy itself is only slightly brighter than the background night sky. Sextans is often described as a ghost of a galaxy, a fragile cloud of ancient stars adrift in the void. Like Sculptor, Sextans is a dwarf spheroidal galaxy, meaning it has a soft, rounded appearance without the spiral arms or glowing disks that larger galaxies often display. Its population of stars is much smaller, only a few 100,000, and most of them are very old. There is almost no trace of ongoing star formation. Sextans appears to have run out of gas long ago, leaving only the pale, steady light of its ancient suns. At first glance, these quiet galaxies may seem dull compared to more dramatic systems like the Sagittarius dwarf, which is being shredded by the Milky Way's gravity, or the Magellanic Clouds, which glow with the fire of new stars. But there is a special kind of value in their calmness. Because they are not being torn apart or disturbed, astronomers can study their internal structure with greater clarity. Their stars have remained largely untouched for billions of years, allowing scientists to reconstruct a clean and simple record of their past. By studying the metallicity, the abundance of heavy elements, in their stars of different ages, researchers can trace how quickly Sculptor and Sextans enriched their gas before star formation stopped. The picture that emerges is one of early growth followed by a long quiet period. Galaxies that were active in the young universe, but soon faded into silence. This shows that not all dwarf galaxies are chaotic or doomed to destruction. Some simply settle into long lives of quiet stability under the watchful gravity of their larger host. In cosmological simulations, small galaxies like Sculptor and Sextans are thought to be the building blocks of larger galaxies. Over time, such dwarfs merge with one another and with massive systems like the Milky Way, contributing their stars to the vast halos that surround big galaxies. Studying the few that still survive today helps astronomers test whether their computer models of galaxy formation are accurate. Because Sculptor and Sextans are relatively simple, scientists can use them to check how gas cools, how stars form, and how galaxies lose their fuel over time. If the models can reproduce galaxies like these, it strengthens confidence in the broader picture of galactic evolution. If not, it means something. Perhaps the way supernova explosions affect gas loss, or how dark matter behaves, needs to be rethought. Indeed, dwarf spheroidal galaxies like these are some of the most mysterious objects in the universe. They appear to contain far more dark matter than normal matter, making them ideal laboratories for studying this invisible substance that shapes the cosmos. In fact, some of the strongest evidence for dark matter does not come from grand spiral galaxies like the Milky Way, but from faint, modest dwarfs like Sculptor and Sextans. Sculptor itself hides another secret. Its stars are arranged in a pattern suggesting two overlapping populations. One group is more concentrated near the centre and slightly richer in metals, while another is more widely spread and metal poor. This hints that Sculptor may have experienced more than one burst of star formation, or perhaps an early collision that stirred its contents. Even in a galaxy that seems peaceful, traces of an active and complicated past remain. Sextans, with its extremely low density of stars, presents its own puzzles. How could such a fragile system have formed in the first place? And how has it managed to survive the Milky Way's powerful tidal forces for so long without being torn apart? These questions keep astronomers returning to those faint smudges of light that, at first glance, seem unremarkable. In the grand portrait of the Milky Way's many satellites, Sculptor and Sextans represent the quiet, understated members of the family. They do not display vast bridges of gas or dazzling clusters of newborn stars. Instead, they persist, dim, ancient and serene, their beauty lying in their simplicity, their endurance, and the silent stories they tell about the early days of our universe. If you were to stand beneath a dark, starry sky and look up with only your eyes, you would never notice the Ursa Minor or Draco dwarf galaxies. They hide in plain sight, so faint that even the clearest night offers no hint of their presence. Only through deep astronomical imaging and highly sensitive instruments do they reveal themselves as delicate clouds of ancient stars, scattered like faint dust against the vastness of space. Yet, despite their quiet and almost invisible appearance, these two tiny galaxies hold a powerful secret. They are overflowing with dark matter, an unseen substance that outweighs their stars by enormous amounts. In fact, few galaxies in the universe show such an extreme imbalance between what can be seen and what cannot. The Ursa Minor dwarf galaxy lies in the northern sky, near the familiar pattern of the Little Dipper. If you could journey there, you would find an ancient gathering of dim stars, most of which were born more than 10 billion years ago. Almost all its gas has long vanished, meaning new stars have not been born there for countless ages. The galaxy now drifts quietly through space, its light the faint echo of a once active past. Draco, its close neighbour, shares a similar fate. Named after the constellation of the Dragon that winds its way across the northern heavens, the Draco dwarf galaxy is another small and ghostly system. Its stars, too, are ancient, silent witnesses to a time when the universe was young. Both Draco and Ursa Minor belong to a family called Dwarf Spheroidal galaxies, systems that have no spiral arms, no brilliant nebulae, and no bursts of star formation. To the casual eye, they seem uneventful, even dull, but their true wonder lies deep beneath the surface. In both galaxies, dark matter reigns supreme. Astronomers estimate that more than 90% of their total mass is made up of this mysterious material. For every shining star, there may be hundreds, perhaps thousands, of invisible dark matter particles forming the true skeleton of the galaxy. Their mass-to-light ratios are staggering, dozens or even hundreds of times greater than that of our Milky Way. In this sense, they are not just small galaxies, they are fortresses of darkness. In the Milky Way, dark matter is mixed together with stars, gas and dust, making it difficult to study. But in tiny galaxies like Draco and Ursa Minor, where there is little else to interfere, the influence of dark matter stands out clearly. They serve as natural laboratories, magnifying glasses that allow astronomers to study how this invisible substance behaves on small scales. This leads to one of the great puzzles in modern cosmology. What exactly does dark matter do inside small galaxies? The standard theory of cold dark matter predicts that galaxies should have dense, sharply peaked centers, where dark matter clumps thickly toward the core. Yet, observations of systems like Ursa Minor and Draco often show flatter centers, where dark matter seems more evenly spread out. This mystery has led scientists to wonder whether our models need improvement, or whether powerful events like ancient supernova explosions might have reshaped the matter inside these galaxies long ago. There is another cosmic puzzle connected to them, known as the too big to fail problem. In computer simulations of the Milky Way's surroundings, many dark matter halos appear that seem massive enough to host bright dwarf galaxies. But when astronomers search the sky, they find far fewer dwarfs than expected. Some halos appear to be entirely dark, massive but invisible. This has raised deep questions about how efficiently stars can form inside small halos, and whether dark matter itself behaves in ways we do not yet understand. Draco and Ursa Minor both lie close to the Milky Way, well within its enormous halo of dark matter, Over billions of years, our galaxy's gravity has tugged at them, stretching and distorting their shapes, just as it is tearing apart the Sagittarius dwarf galaxy today. And yet, despite these relentless forces, Draco and Ursa Minor have survived. Their endurance suggests that their dark matter halos are especially dense, serving as invisible armor that keeps them from being torn apart entirely. In the grand story of the universe, these dwarfs may be among the oldest survivors. According to simulations, small dark matter halos were the first structures to form after the Big Bang, later merging together to create larger galaxies like the Milky Way. The dwarfs that remain today are thought to be relics of that ancient era, tiny fossils from the universe's earliest chapters. By studying Draco and Ursa Minor, scientists can glimpse what the building blocks of galaxies looked like more than 10 billion years ago, long before our Milky Way became the magnificent spiral we know today. Both galaxies were first discovered in the 20th century, after long and patient surveys of photographic plates. In the modern age, wide-field digital cameras and powerful telescopes have allowed astronomers to study them in far greater detail, mapping their stars one by one and tracing the faint halos that stretch beyond their visible edges. Even so, they remain elusive, visible only through long exposures and sensitive detectors. They may appear to be nothing more than dim smudges against the darkness of space, but Draco and Ursa Minor are anything but insignificant. Hidden within their faint glow lies a cosmic secret, a story about the invisible matter that shapes galaxies, binds the universe together, and continues to challenge everything we think we know about the cosmos. If the large and small Magellanic Clouds are the bright, obvious companions of the Milky Way, then the Bootes dwarfs and the so-called ultra-faint dwarfs are their complete opposites. These are not shining jewels of the night sky, but fragile whispers of galaxies, so dim that even the most powerful telescopes struggle to find them. They hide just beyond the edge of visibility, like cosmic ghosts lost in the deep darkness of space. When astronomers first began to discover them, many wondered if these faint collections of stars could even be called galaxies at all. Some of them contain only a few thousand stars, sometimes just a few hundred, spread thinly across space, like scattered embers fading from a dying fire. The first of these discoveries came in the year 2006, when astronomers detected the Bootes dwarf galaxy. It was the first real glimpse into what these ghostly companions of the Milky Way looked like. Among the group, Bootes 1 is the brightest, though even it shines with a faintness that makes it nearly invisible compared to galaxies such as Fornax. The stars within Bootes 1 are among the most ancient and chemically primitive ever observed, holding the signatures of an early universe untouched by later generations of star formation. After Bootes 1 came Bootes 2, an even fainter, more delicate neighbour. Bootes 2 is so small and dim that astronomers debated whether it should even count as a galaxy, or merely as a loose cluster of wandering stars. Its stars are widely spread apart, and the system appears to be stretched and pulled by the Milky Way's immense gravity. Yet, despite its fragile appearance, Bootes 2 carries an extraordinary secret. When scientists studied the movements of its stars, they realized that the system's total mass was far greater than the visible stars could explain. This hinted that Bootes 2 too must be enveloped by a vast halo of dark matter. If that is true, then Bootes 2 is not just a simple star cluster. It is a true galaxy, one whose few remaining stars are held together only by the invisible hand of dark matter. This discovery opened the floodgates. As astronomers began conducting deeper and more detailed sky surveys, they found more and more of these ghost-like companions scattered throughout the Milky Way's outer halo. These fragile systems were named ultra-faint dwarfs, a fitting title for galaxies that seem to hover on the very edge of existence. Unlike the brighter dwarf galaxies such as Fornax, these ultra-faints only appear in the most careful sky surveys, where astronomers sift through billions of stars to find tiny clumps moving together through space. Each new discovery added another faint and ancient member to the Milky Way's growing family of companions. Many of their stars are believed to have formed more than 12 billion years ago, during the universe's first great burst of star creation after the Big Bang. Unlike larger galaxies that experience several generations of starbirth and chemical enrichment, the ultrafaints stopped forming stars very early. Their stars remain frozen in time, poor in heavy elements and still reflecting the universe's earliest chemistry. One of the most remarkable examples is Segue 1, a galaxy so dim that it emits less light than a single bright star. For years, astronomers debated whether it was truly a galaxy or just a random gathering of stars. But careful study revealed that its stars move in ways that can only be explained by the presence of unseen mass. Once again, dark matter. Even more striking is the composition of its stars, which are among the most metal-poor ever discovered. They are relics of the first generation of stars, making Segue 1 not just a ghost of a galaxy, but a fossil from the dawn of cosmic history. Another ultra-faint Reticulum 2 astonished astronomers when they found that its stars were unusually rich in heavy elements, created by rare and violent neutron star mergers. This was unexpected, since such tiny galaxies were thought to be too small to hold on to the debris of such explosive events. Yet Reticulum 2 showed that even the smallest galaxies can preserve traces of cataclysmic events, adding new chapters to the story of how the universe's elements were forged. Each ultra-faint dwarf tells its own tale, and together they form a mosaic of the early cosmos. Astronomers still puzzle over why some dark matter halos host thriving galaxies, while others end up as nearly invisible ghosts. The leading idea is that the smallest halos formed stars early on, but as the first generations of stars ignited, they filled the cosmos with fierce radiation that heated and stripped gas away from these tiny galaxies. Without gas, they could no longer form new stars, leaving only the sparse ancient ones behind. In this way, the ultra-faint dwarves are survivors of a cosmic purge, remnants from a time when only the largest halos could keep their gas and continue to shine. They are more than faint specks in the sky. They are living fossils from the universe's earliest age, silent witnesses to the dawn of galaxies. Even now, astronomers believe that many more of these shadowy galaxies may still be hidden in the faintest corners of the sky. Each new discovery brings theory and observation a little closer together, helping us understand not just the Milky Way's family of companions, but the deep and mysterious story of how the first galaxies came to be. If you gaze toward the constellation of Canis Major, the greater dog in the night sky, you are looking into one of the most mysterious and hotly debated regions in our part of the universe. In this direction lies what astronomers call the Canis Major overdensity, a curious clump of stars that has puzzled scientists ever since it was first noticed in the early years of the 21st century. Unlike the clearly defined Magellanic Clouds or the Sagittarius Dwarf Galaxy, this structure does not easily fit into any category. Is it truly a small galaxy being swallowed by the Milky Way, or is it merely a ripple, a natural wave of stars within our galaxy's vast spiral disk? The story of the Canis Major overdensity began when astronomers were mapping the distribution of stars across the sky using wide surveys. When they turned their instruments toward Canis Major, they found something unusual, a dense patch of stars lying just beyond the Milky Way's thick disk. These stars seemed to move in their own distinct way, suggesting that they might belong to a separate system rather than to the Milky Way itself. The idea was thrilling. If true, it would mean that our galaxy was in the process of consuming yet another small companion galaxy, a cosmic act of galactic cannibalism unfolding right before our eyes. What made the discovery even more exciting was its closeness. The Canis Major structure appeared to lie only about 25,000 light-years from Earth, far nearer than most known dwarf galaxies. The thought of a neighbouring galaxy hiding practically within the Milky Way's own body captured everyone's imagination. Observers even detected a huge, faint arc of stars known as the Monoceros Ring, looping gracefully around the Milky Way's outer disk. Some astronomers believe this ring to be the torn and scattered remains of the Canis Major system, stretched out by the Milky Way's immense gravity, just as the Sagittarius Dwarf Galaxy is being ripped apart. For a time, the evidence seemed strong. But, as often happens in astronomy, the more scientists looked, the more complicated the picture became. Some researchers pointed out that the Milky Way's disk is not flat and smooth like a record, but warped and rippled like a sheet of fabric stirred by wind. Such natural bends and waves could easily create regions that look like dense clusters of stars when viewed from our position on Earth. In that case, the Canis Major overdensity might not be a separate galaxy at all, just a trick of perspective, a local gathering of stars shaped by the Milky Way's own motion. This disagreement gave rise to one of the most persistent debates in modern galactic astronomy. Is Canis Major a galaxy or a ripple? Different studies have reached different conclusions. Some surveys found stars in the region that appear older and poorer in heavy elements, the kind of stars usually found in dwarf galaxies that evolve separately. Other studies, however, showed that these stars match the traits of ordinary Milky Way disk stars, suggesting that the overdensity is simply a dense patch within our own galaxy's structure. One problem is that the Canis Major region sits in a very crowded part of the sky. When astronomers peer in that direction, they must look through vast layers of gas, dust, and millions upon millions of foreground stars. This thick veil makes it extremely difficult to tell which stars belong to the overdensity and which are part of the Milky Way's ordinary disk. Unlike the bright Magellanic Clouds that shine clearly against the dark southern sky, Canis Major blends almost seamlessly into the Milky Way's glowing background. Only through careful measurements of how stars move and what elements they contain can astronomers begin to separate one structure from another, and even then, the answers remain uncertain. If Canis Major truly is a separate galaxy, it would mean we are witnessing the Milky Way in the act of devouring a close companion. Its scattered stars, forming part of the Monoceros ring, would stand as silent witnesses to the slow and dramatic process by which great galaxies grow, not through peaceful expansion, but by absorbing smaller ones. The Milky Way's halo, already full of faint streams and remnants of long-lost galaxies, would gain another name on its list of celestial victims. But if the Canis Major overdensity is not a galaxy at all, if it is simply a ripple within the Milky Way's own disk, that would be just as fascinating. It would mean that our galaxy is far more dynamic and alive than we once thought. Waves, rings, and ripples could be the scars left by ancient collisions, perhaps caused by other dwarf galaxies plunging through the Milky Way's plane long ago and disturbing its stars. In this view, Canis Major might not be a galaxy itself, but rather the echo of one, the faint footprint of a past encounter that still ripples through the stars today. Even though it lies relatively close to us, only tens of thousands of light years away, the Canis Major overdensity reminds us how much we still do not understand about our galactic home. The boundary between a small galaxy and a dense region of the Milky Way is not always clear. Galaxies are not tidy, round islands of stars. They blend and overlap, twisting into streams, rings, and cloudy patches where one fades into another. Whether the Canis Major overdensity proves to be a separate galaxy being devoured, or simply a natural wave in the Milky Way's disk, it remains a remarkable discovery. Its study helps astronomers understand how galaxies change, through both the calm settling of stars and the violent tearing apart of their companions. It sits in the grey zone between order and chaos, between galaxy and ripple, showing that our cosmic neighbourhood is not simple or static, but full of motion and mystery. Perhaps one day, with sharper instruments and deeper surveys, astronomers will finally uncover the truth. Until then, the Canis Major overdensity remains a cosmic enigma, a shimmering question mark written in the stars, where the boundary between what is ours and what is other fades into the light of the Milky Way itself. The European Space Agency's Gaia mission was not just another telescope in space, it was a time machine, a detective, and a historian all in one. Launched with the goal of mapping the Milky Way, Gaia was built to do far more than simply show where stars are. It was designed to reveal how they move, how they were born, and how our galaxy grew from countless ancient collisions. From Gaia's work, an entirely new science has emerged: Galactic Archaeology, the study of our galaxy's history through the motions of its stars. But instead of digging into the Earth, astronomers now dig through the sky, uncovering the ghosts of long-lost galaxies that were swallowed by the Milky Way billions of years ago. Gaia's power lies in its extraordinary precision. It measures parallax, a tiny shift in a star's position as the Earth moves around the Sun. This shift is so small that it's like spotting a hair move at the distance of 1,000 kilometers, yet it allows astronomers to measure the distances to stars with astonishing accuracy. But Gaia doesn't stop there. It also measures each star's proper motion, the slow drift of a star across the sky, as well as its radial velocity, the speed at which it is moving toward or away from us. When all of this information is combined, Gaia creates a three-dimensional map showing how millions of stars travel through the Milky Way like dancers moving to invisible cosmic rhythms. Before Gaia, much of our galaxy was a mystery. Many of its faintest companions, small dwarf galaxies and thin rivers of stars called stellar streams, were nearly impossible to see. They blended into the background like whispers in a crowd. But Gaia changed everything. With its data, astronomers could suddenly pick out stars that moved together, revealing hidden patterns and shared origins. Entire systems that were invisible before now stand out clearly, their common motions exposing their ancient ties. One of Gaia's most remarkable discoveries was the evidence for a colossal collision known as the Gaia Enceladus merger. This was not a small dwarf galaxy quietly orbiting at the edge of the Milky Way. It was a massive system, possibly 1/4 of the size of our own galaxy, that smashed into the Milky Way about 10 billion years ago. The proof did not come from simply counting stars, because there was no clear bright patch announcing, "Here lies a galaxy." Instead, astronomers noticed that many stars in the Milky Way's halo were moving on long, stretched-out orbits, diving in and out of the galaxy like comets. These stars also had a distinct chemical makeup. They were poorer in heavy elements than stars that formed in the Milky Way's main disk. Together, these clues told a story of a great ancient merger, one that shook the Milky Way and helped form its thick disk. Without Gaia's precise motion measurements, those stars would have remained hidden, lost in the crowd of billions. Before Gaia, astronomers could only find nearby companions if they were dense and bright enough, like the Fornax or Sculptor dwarf galaxies. But most mergers left behind only faint traces, thin streams of stars scattered through the halo. These traces are almost invisible in ordinary star maps, but motion tells a different story. A star that once belonged to a captured galaxy never forgets how it used to move. Its orbit is like a fingerprint that survives long after its home galaxy has vanished. Gaia allows astronomers to read those fingerprints. By mapping how stars move, it becomes possible to group them into families, some forming graceful streams, others revealing the scattered remains of entire galaxies that long ago were absorbed into the Milky Way. Another of Gaia's great contributions is the discovery of the Helmi streams, named after the astronomer Amina Helmi, who first identified them. These are groups of stars travelling together through the halo, no longer bound by gravity but united by a shared past. Their orbits and chemical compositions point to a single dwarf galaxy that was devoured between 6 and 8 billion years ago. These stars were invisible on a normal map, blending into the cosmic background, but in Gaia's motion data they appeared like arrows all pointing in the same direction, evidence of their common origin. Gaia has also revealed that even the Milky Way's main disk is not calm and flat. Instead, it ripples and bends like a warped vinyl record. Some stars bounce up and down through the galactic plane, disturbed by the gravitational tugs of smaller galaxies passing by, perhaps the Sagittarius dwarf galaxy, or others that have brushed past over time. These ripples are the scars of ancient encounters, showing that the Milky Way is still evolving today. It is not a quiet, settled structure, but a living, breathing system, shaped and reshaped by its history. In the past, astronomers identified new galaxies mostly by spotting clusters of stars, bright concentrations in the sky that stood out from the background. But Gaia has revealed that some of these so-called clusters are not galaxies at all, but the shredded remains of larger systems long since torn apart. Others that seemed like scattered stars in the halo turned out to be faint dwarf galaxies hiding in plain sight. Gaia's motion data separates these tangled populations, turning what used to be a still photograph of the sky into a moving film where the relationships between stars suddenly become clear. By combining motion with chemical analysis, astronomers can now trace where stars were born and when they joined the Milky Way. Stars formed in massive galaxies tend to be richer in metals, while those from smaller ones have fewer heavy elements. When this chemical information is combined with orbital data, astronomers can reconstruct the sequence of mergers that built our galaxy. The stars of Gaia Enceladus, for instance, point to a collision around 10 billion years ago, while other stellar streams record smaller mergers that happened more recently. Bit by bit, Gaia is helping to assemble the Milky Way's family tree, a cosmic ancestry chart showing all the galaxies that came together to make the one we live in today. Gaia's data also provides clues about something even more mysterious: dark matter. The way stars move, especially those from old mergers, reveals the shape of the invisible halo of dark matter that surrounds our galaxy. If their orbits do not match what visible matter alone can explain, it means something unseen, something massive, is influencing their paths. By studying these stellar motions, astronomers can probe the hidden skeleton of dark matter that holds the Milky Way together, and Gaia's story is far from over. With every new release of data, millions more stars are added to its map, each measured with even greater precision. Astronomers have already identified several past mergers, each with its own population of stars and its own name, like Sequoia, Tamnos, and Arjuna. Each of these represents a galaxy that once existed, now gone except for its scattered stars drifting through space. The faint dwarf galaxies we can still see today, like Sculptor and Fornax, are just the survivors of a much larger family. Many others vanished long ago, leaving behind only faint trails, ripples, and odd motions. In the study of galaxies, and especially the smallest and faintest ones known as dwarf galaxies, one mystery has puzzled astronomers for decades: the strange way that dark matter seems to arrange itself. Theoretical models and computer simulations tell us one thing, but real observations often tell us another. This mismatch between what scientists expect and what they actually see is called the cusp core problem. According to theory, dark matter should gather very densely toward the centre of a galaxy, forming a steep pointed region known as a cusp. But when astronomers look closely at real dwarf galaxies, they often find something quite different: a smoother, flatter central area known as a core. In other words, instead of dark matter forming a sharp spike in density, it seems to spread out evenly near the centre, creating a gentler slope. The origins of this puzzle go back to the late 20th century, when scientists first began running large cosmological simulations. Using the idea of cold dark matter, particles that move slowly and interact only through gravity, they modelled how the universe grew and how galaxies formed. These early simulations revealed that dark matter tended to clump together into halos, with the material becoming denser and denser toward the middle. This predicted structure, with its steep central rise, became known as the cusp. As computer power improved and simulations became more detailed, these cuspy centres appeared again and again. It seemed that sharp cusps were not just quirks of early models, but natural features of how cold dark matter behaves. However, when astronomers turned their telescopes toward the real universe, the evidence told a different story. In many dwarf galaxies, the motions of the stars showed that dark matter did not bunch up tightly in the centre. Instead, the density seemed to level off, forming a flat core. To imagine this difference, picture a steep hill compared to a wide plateau. The cusp is the hill, rising sharply and peaking at the top. The core, by contrast, is the plateau, broad and level before gently dropping off. In large galaxies such as the Milky Way, the situation is complicated because stars, gas, and black holes all affect the gravitational balance. But in dwarf galaxies, where there is very little visible matter, the influence of dark matter stands out more clearly. Over and over, observations of these faint galaxies have shown cores instead of cusps. This is a serious problem for theory. If dark matter really behaves as cold, collisionless particles that interact only through gravity, then cusps should form naturally. The fact that so many dwarfs show cores suggests that something is missing. Either our understanding of galaxy formation is incomplete, or dark matter itself behaves differently than we thought. To solve the mystery, scientists have explored two main possibilities. One focuses on astrophysical processes within galaxies themselves. Even though dwarf galaxies have few stars, those stars can still make a big impact. When massive stars die as supernovae, they release tremendous energy, pushing gas outward from the centre. If this process happens again and again over millions or even billions of years, it can stir up the galaxy's inner structure. The gravitational pull changes slightly each time, causing dark matter to move outward and spread more evenly. Over long periods, these repeated bursts of energy can transform a sharp cusp into a smooth core. Modern simulations that include not just dark matter, but also gas, stars, and the feedback from their activity, often produce galaxies with cores that look much like what astronomers observe. This suggests that the cusp core problem might not mean that dark matter theory is wrong, only that early models were too simple and ignored the messy physics of real galaxies. Yet this explanation does not satisfy everyone. Some dwarf galaxies appear to have very little recent star formation, and still they show evidence of cores. Others would require far more energy from supernova explosions than seems reasonable, given their small number of stars. For these galaxies, feedback from star formation alone may not be enough. This has led researchers to a more radical idea, that dark matter itself might not behave exactly as the cold, collisionless version predicts. Perhaps dark matter particles can occasionally interact or collide with each other. This concept is known as self-interacting dark matter. If dark matter particles occasionally bump into one another, even very gently, those interactions could over time redistribute the particles, smoothing out cusps into cores. This kind of dark matter still fits many of the successes of cosmology, but it can also explain why some galaxies look the way they do. Another intriguing possibility is that dark matter is made of extremely light wave-like particles. In this fuzzy dark matter idea, the quantum nature of these ultralight particles causes them to spread out, resisting the formation of sharp peaks in density. The result would be naturally soft, smooth cores at the centres of galaxies. Both of these ideas, self-interacting dark matter and fuzzy dark matter, are appealing because they can explain the observed structures of dwarf galaxies without requiring intense bursts of star formation. But they also create new challenges. If dark matter interacts too strongly, or if it is too fuzzy, it could change the shapes and motions of much larger galaxies, which we already understand quite well. So, scientists must tread carefully, searching for theories that solve the cusp core problem without breaking other parts of cosmology. Meanwhile, observations continue to improve, with new instruments capable of measuring the tiny motions of individual stars in faint dwarf galaxies. Astronomers can now build more accurate maps of how mass is distributed within them. Radio telescopes, which trace the motion of gas, provide another way to test the predictions. Yet even with all this data, the story remains complex. Some dwarf galaxies clearly show smooth cores, while others seem to preserve sharp cusps. This variety may mean that there is no single, universal answer. Instead, each dwarf galaxy may have followed its own path. A galaxy that experienced violent bursts of star formation could have flattened its dark matter into a core, while one that evolved more quietly might still retain its cusp. In this way, the cusp core problem may not be a strict contradiction at all, but rather a window into the many different ways that galaxies can grow and change across the vast history of the universe. Unlike the bright spiral arms that wind gracefully around the Milky Way, or the crowded glowing heart at its centre, the galactic halo is a faint and ghostly region. It spreads out in every direction, stretching far beyond the visible disk of the galaxy. At first sight, it seems almost empty, a thin mist of light in the darkness of space. But hidden within that dim glow lies a silent record of the Milky Way's long and turbulent history. The halo is made up of lonely stars, ancient globular clusters, and the scattered remains of galaxies that once lived independent lives before being drawn in by the Milky Way's immense gravity. Most scientists now agree that much of the outer halo did not form within the Milky Way at all. Instead, it was built from the wreckage of many smaller galaxies that were pulled apart and absorbed over billions of years. This idea, that the halo is like a cosmic graveyard filled with the ghosts of long-lost galaxies, first began to take shape in the late 20th century. Even then, astronomers noticed something unusual. The stars in the halo were not like the ones in the galactic disk. Halo stars are very old and poor in heavy elements, what astronomers call metals. In contrast, the stars in the Milky Way's disk are younger and richer in metals, constantly renewed by the births and deaths of generations of stars. Supernova explosions spread new elements through the disk, but the halo seems frozen in time, unchanged for billions of years. The mystery found its answer in dwarf galaxies, tiny, fragile systems that often run out of gas early and stop forming new stars. These dwarfs rarely produce heavy elements, so their stars remain chemically simple. When a giant like the Milky Way captures and tears apart such a dwarf, its stars are scattered through space, adding to the halo. The result looks exactly like what we see today, an ancient, faint and metal-poor population of stars drifting in the galaxy's outskirts. As telescopes and sky surveys improved, astronomers began to find real evidence of these galactic feasts. They discovered long curving rivers of stars, tidal streams, stretching across the sky, along with odd clumps of stars moving in strange orbits. These are the fading scars of past mergers. Over time, such features blur and blend into the background, but the process is so slow that even after more than 10 billion years, many traces remain visible. By carefully mapping the stars and measuring their motions, scientists can still tell where one ancient galaxy once ended and another began. In this way, the halo can be seen as a great cosmic quilt, stitched together from countless smaller galaxies. Each dwarf that fell into the Milky Way left behind more than just its stars. It contributed its dark matter, its globular clusters, and its unique chemical signature. When astronomers study halo stars with powerful instruments called spectrographs, they sometimes find strange mixtures of elements that don't match typical Milky Way stars. These chemical patterns act like identity cards, showing which stars were born in foreign systems. By gathering and comparing these chemical passports, scientists are able to piece together the Milky Way's past, tracing how many galaxies were swallowed and when. Today, astronomers believe the Milky Way's halo was built in two great phases. The inner halo, which lies closer to the galactic centre, seems to have formed partly from within the Milky Way itself and partly from a few large mergers. The outer halo, which stretches hundreds of thousands of light-years into space, is far more chaotic. A vast sea of stars from many smaller galaxies that once drifted freely through the universe. The difference between the inner and outer halo became especially clear thanks to the European Space Agency's Gaia mission, which began mapping the positions and movements of over 1 billion stars in the 21st century. One of its most striking discoveries was the Gaia-Enceladus merger, a colossal event billions of years ago that left behind a sausage-shaped pattern in the motions of stars. Another major contributor was the Sagittarius dwarf galaxy, which is still being torn apart today. But these are only the largest examples. Dozens of other dwarfs have vanished completely, leaving only their stars scattered across the halo like dust. Computer simulations now confirm this grand picture. Large galaxies like the Milky Way grow by devouring smaller ones, and their halos preserve the memory of that growth. Many of the globular clusters orbiting in the Milky Way's outskirts have chemical signatures showing that they did not form here at all. They are survivors from destroyed dwarf galaxies, still intact even after their parent systems were shredded. By comparing the orbits and chemical makeup of these clusters, astronomers can even group them into families, clusters that once shared the same lost home. The dark matter that surrounded those dwarfs also merged with the Milky Way's own dark matter halo, blending into the invisible skeleton of our galaxy. If this is true, then even the unseen structure that holds the Milky Way together is shaped by the ghosts of smaller galaxies, and the process has not stopped. The Milky Way continues to pull on nearby dwarfs, slowly drawing them inward. In the distant future, their stars will be scattered across the halo, joining the countless others that came before. Each one will add its own faint thread to the Milky Way's great cosmic tapestry. The halo, then, is not just a region of empty space. It is the galaxy's memory, a glowing archive of all the galaxies that came together to form our own. The Milky Way, like every great spiral in the universe, is a mosaic made from the remnants of many smaller worlds, bound forever in a shared destiny of light, gravity, and time. Stars in dwarf galaxies often tell a story very different from the one written in the Milky Way. When astronomers study these tiny, faint galaxies, they find that the elements inside their stars do not follow the same patterns seen in our own galaxy. The differences are especially striking when we look at the balance between what scientists call alpha elements, things like magnesium, calcium, and silicon, and iron. In the Milky Way, older stars tend to have large amounts of alpha elements compared with iron. This is because, in the early days of our galaxy, huge stars lived fast and died young, exploding as powerful supernovae that spread these elements across space. Later, smaller and longer-lived stars also began to explode, but through a different kind of event called a Type Ia supernova. These added more iron to the mix, changing the balance over time. In dwarf galaxies, however, this change in the chemical balance happens much earlier, at much lower overall metallicity. That is, when the stars still contain very little of the heavier elements. This shows that dwarf galaxies form stars far more slowly and much less efficiently than the Milky Way. Because of that, Type Ia supernovae start to shape their chemistry sooner. Every dwarf galaxy, therefore, keeps a record of its own slow and uneven rhythm of growth. By studying the unique chemical fingerprints of these stars, astronomers can even identify which stars in the Milky Way originally came from smaller galaxies that were later absorbed into it. Some of the most valuable clues come from elements heavier than iron. These heavy elements are created in two special ways: the slow process, or S process, which takes place inside old, swollen giant stars, and the rapid process, or R process, which happens during extreme cosmic events such as the collision of neutron stars or the explosion of very massive stars. Dwarf galaxies show strange patterns in these heavy elements. Some contain very few of them, meaning that those rare events almost never happened there. Others, however, show sudden and dramatic spikes in the presence of R-process elements, signs of a single powerful event that enriched the entire galaxy. One remarkable example is the ultra-faint dwarf galaxy called Reticulum 2. Its stars contain extraordinary amounts of R-process material, which suggests that long ago a single neutron star merger might have filled the whole galaxy with heavy elements. Discoveries like this show that even in the smallest, faintest galaxies, one event can leave a lasting mark that is still visible billions of years later. In the Milky Way, such chemical traces are blurred by the mixing of billions of stars over billions of years, but in dwarf galaxies they remain clear and untouched. That is why astronomers treasure these tiny galaxies. They act as natural laboratories for studying nucleosynthesis, the process by which stars create elements. Some stars in dwarfs appear to be among the oldest and most primitive in the entire universe. Their chemical fingerprints offer a direct window into the distant past, back more than 13 billion years, to the time when the very first supernovae spread elements heavier than hydrogen and helium into space. Studying such ancient stars allows astronomers to trace how the universe itself began to grow more complex. The way dwarf galaxies form stars also reveals much about their chemistry. The Milky Way's enormous mass allows it to trap gas and recycle it, forming new stars continuously. But in a dwarf galaxy, even a small burst of star formation can blow away much of its gas, shutting down the process for hundreds of millions of years. During these quiet times, no new stars form, and the leftover gas becomes chemically altered by the products of old supernovae. When the galaxy finally resumes forming stars, the new generation carries a different chemical signature. This stop-and-start rhythm gives dwarf galaxies their strange and beautiful patterns of element ratios. Astronomers also use a method called chemical tagging, which assumes that stars born from the same cloud of gas share the same chemical fingerprint. In large galaxies, this is difficult to do because so many stars overlap in chemical space. But in dwarfs, with their small and simple populations, it becomes possible to trace families of stars back to their origins. This has revealed whether a dwarf experienced one major burst of star formation, or many small ones, and how encounters with the Milky Way might have changed its destiny. Modern surveys like Apogee and DC are now collecting the chemical fingerprints of millions of stars, giving astronomers an ever sharper picture of galactic ancestry. By comparing these patterns, they are building a kind of family tree for the Milky Way and its companions. Dwarf galaxies, with their odd and sometimes extreme mixtures of elements, are proving to be the keys to understanding how galaxies grow, how elements are forged, and how the universe built the rich diversity of matter we see today. And yet, the Milky Way's story is not complete. Many of its smaller companions still remain invisible. Astronomers believe that a whole swarm of unseen dwarf galaxies is still waiting to be found, hiding in the shadows around us. To uncover them, scientists need sharper eyes, better telescopes and smarter ways to read the data. They must separate true patterns from random noise and recognize when a faint clump of distant stars is, in fact, a galaxy of its own. Each new dwarf that is discovered reshapes our understanding of how the Milky Way formed, how its stars grew, and how dark matter shaped the structure of our cosmic neighborhood. If the predictions are right, most of our galaxy's satellites have yet to be detected. New surveys covering vast stretches of the sky will help fill in the missing pieces. Astronomers are especially excited about the Vera C. Rubin Observatory, which is expected to begin full operations in the late year 2025. Its powerful and repeated scans of the heavens will likely reveal faint dwarf galaxies that have been overlooked, filling in the Milky Way's family map with new and unexpected members. Some of these hidden dwarfs might even be lurking behind the bright band of the Milky Way's disk, where their faint light is drowned out by countless nearby stars and clouds of interstellar dust. Finding them will not be easy, but every discovery brings us closer to a complete picture of how our galaxy, and the universe itself, came to be. The dazzling glow of starlight and the hazy veil of cosmic dust make it extremely hard for astronomers to tell a small satellite galaxy apart from the bright background of the Milky Way. Because of this, many of the missing dwarf galaxies might actually be hiding in plain sight, buried in regions of the sky that are difficult to study. To uncover these hidden companions, astronomers have to look for clever new ways to see through the dusty clouds and brilliant light, using tools that detect infrared light, which can pierce through cosmic haze far better than ordinary visible light. Yet there is another, even more mysterious possibility. Some of the unseen dwarves might not just be faint, they might be almost completely dark. These would be galaxies where dark matter outweighs normal matter to such a degree that hardly any stars exist to give off light. If such ghostly objects are real, they would be nearly impossible to detect directly. The only way to find them would be by their gravitational fingerprints, the subtle ways they tug on streams of stars in the Milky Way's halo, or disturb the gentle motion of gas at the edge of our galaxy. Already, astronomers have been astonished by what they have found in the past 20 years. Some dwarf galaxies are so faint that they contain fewer stars than an ordinary star cluster. One example is Segue 1, a tiny system that glimmers weakly, but has a mass almost completely made of dark matter. Others, like Crater 2, are surprisingly large but so diffuse that their stars are spread thinly over a huge area, making them glow only faintly at the centre. These discoveries show that the missing satellites are not simple or uniform objects. They come in many strange shapes and structures, forcing scientists to rethink what a dwarf galaxy even is. The search for these mysterious companions doesn't stop with the Milky Way. It extends outward to our nearest large neighbour, the Andromeda Galaxy, which already has its own rich collection of satellites. Some of Andromeda's smaller companions are oddly arranged in narrow planes, almost like beads on invisible strings, a pattern that still puzzles astronomers. Yet, even around Andromeda, many predicted satellites remain unseen. The same is true for the Triangulum Galaxy, another nearby spiral. If this shortage of small galaxies appears everywhere, then it suggests a deeper mystery, one tied to how small galaxies form across the entire universe, not just in our own corner of space. A little more than 100 years ago, no one even knew dwarf galaxies existed. Only as telescopes and sky surveys became more powerful did these tiny companions begin to reveal themselves one by one. Each new generation of instruments has peeled back another layer of the cosmic curtain, uncovering ever fainter and more elusive systems. This means that our picture of the universe is always unfinished. The galaxies we haven't found yet may simply be waiting for the next great leap in technology. In this way, the mystery of the missing dwarfs is not just about the galaxies themselves, it is also about the limits of human observation. If future discoveries uncover many more ultra-faint dwarfs, the number of known satellites could finally match what theory predicts, helping to solve the long-standing missing satellites problem. But if, even with improved instruments, the count still falls short, then it might mean that our understanding of how galaxies form and evolve is missing something important. Either outcome would be revolutionary. Some of the unseen dwarfs may not be missing at all. They might have been destroyed by the Milky Way long ago. Their stars could now be drifting as scattered streams through the galactic halo, and their dark matter halos may have merged into our galaxy's larger structure. If this is true, then the lost companions are not gone. They are ghosts, their remains stretched thin across the sky, stripped of everything that once made them shine. This process of destruction often begins when a small galaxy loses its gas, the vital ingredient for star formation. Gas is the fuel that allows new stars to be born. Without it, a galaxy slowly fades, becoming a quiet place where old stars die out and no new ones take their place. Many dwarf galaxies near the Milky Way are almost completely devoid of gas, looking barren and lifeless compared to what we think of as normal galaxies. One major reason for this emptiness is a process called ram pressure stripping. To picture how it works, imagine a car speeding down a highway with the windows open. The rushing air blows against everything inside, trying to push it out. Now, replace the car with a small galaxy, and the air with the thin, hot gas that fills the space between galaxies, the Intergalactic Medium. As the dwarf galaxy moves quickly through this medium, the gas inside it feels the pressure, and if the force is strong enough, it is pushed out into space. This can happen dramatically when a satellite galaxy plunges through the halo of hot gas surrounding a giant galaxy like the Milky Way. The stars, being heavier, mostly stay behind, but the gas, the galaxy's lifeblood, is stripped away. Over billions of years, this process has left many dwarf galaxies in our local group bone dry and starved of the material needed for growth. Some of them may once have looked like the large Magellanic Cloud, bright and full of gas, but repeated passages through the Milky Way's halo gradually peeled them apart, leaving only faint glows of ancient stars. One of the most powerful forces shaping small galaxies is something known as tidal stripping, a process driven entirely by gravity. When a small galaxy orbits around a much larger one, the uneven pull of gravity between its near and far sides stretches it apart. This difference in gravitational pull creates enormous stress that can slowly tear away stars from the smaller galaxy. The gas inside it is even more fragile. It can be pulled away far more easily, like mist caught in a strong wind. Sometimes the very heart of the dwarf galaxy remains untouched, holding on to a few stars at its centre, while the gas and the outer layers of stars are peeled away like the skin of a fruit. What is left behind is a faint ghost-like remnant of the original galaxy, still circling its larger companion, a shadow of what it once was. But the story does not end there. A galaxy can also harm itself from within. The process of star formation is not gentle. It is violent and full of energy. When new generations of massive stars are born, many of them soon explode as supernovae, blasting their surroundings with immense energy and shock waves. In a large galaxy, gravity is strong enough to hold much of this gas in place, but in a small, delicate dwarf galaxy, the gravitational pull is far weaker. The force from exploding stars can easily push gas outward, and once the gas drifts far enough away, other forces, like ram pressure or tidal stripping, can remove it forever. This self-inflicted loss makes it even harder for dwarf galaxies to keep their gas and continue forming new stars. A spectacular version of this can be seen in jellyfish galaxies. These are not dwarves, but larger galaxies travelling through dense clusters of hot gas. As they move, long glowing tentacles of gas are ripped away from them, trailing behind like the arms of a jellyfish. The same thing happens to dwarf galaxies, but on a smaller scale. When a dwarf passes too close to the hot gas halo of a massive galaxy or cluster, it can leave behind thin, wispy trails of gas. Sometimes these trails even sparkle faintly as new stars are born within them, the final traces of what the galaxy once could have been. In our local group of galaxies, astronomers can see this process happening with their own eyes. Dwarf satellites such as Sculptor, Draco and Ursa Minor orbit close to the Milky Way, and they have been stripped again and again until almost nothing is left except their skeletal remains of stars. Other dwarfs, still rich in gas and drifting in from the outskirts, slowly lose their material as they fall deeper into the Milky Way's vast halo. Interestingly, the Andromeda Galaxy, our giant neighbour, might be even more destructive. Its halo of hot gas seems to be broader and heavier than the Milky Way's, giving it a stronger stripping effect. Around Andromeda, faint streams of stars can be seen stretching across space, silent proof that entire galaxies are being pulled apart and scattered into its outer halo. Over billions of years, these processes act like cosmic natural selection. The dwarfs that venture too close to a large galaxy are slowly robbed of their ability to make new stars. Some manage to survive as dim satellites, their structure mostly intact but their future growth halted. Others are shredded completely, their stars forming glowing streams that blend into the halo of the larger galaxy. The gas and stars torn away are not wasted though. They help feed and build the host galaxy, creating new stars and expanding its halo. The destiny of a dwarf galaxy depends on many things: where it orbits, how fast it moves, and how much gas it had in the beginning. A dwarf that keeps its distance might preserve its gas and continue forming stars for billions of years. But one that plunges deep into a giant galaxy's halo may lose everything in just a few close passes, fading into an ultra-faint remnant barely holding itself together. These remnants show us what happens at the very end of the stripping process, the last surviving fragments of once-living galaxies. This raises an even more fascinating question. If the Milky Way has satellite galaxies, could those satellites have satellites of their own? Could the cosmic hierarchy go one step further, forming what might be called sub-sub-galaxies? Is there a natural limit to how small a galaxy can get before it can no longer exist? When astronomers run large computer simulations of the universe, they include all the main ingredients: dark matter, gas, radiation, and the laws of physics that control them. The result is a vast cosmic web, full of filaments and knots where galaxies form. Zooming in closer, scientists see halos of dark matter that host galaxies, and inside those halos, smaller halos that host smaller galaxies. Theoretically, this process could go on indefinitely, halos within halos within halos, like a set of Russian nesting dolls. If this model is correct, then a dwarf galaxy such as Fornax or Sculptor might itself have tiny companions, little galaxies orbiting a slightly larger, yet still modest parent. However, finding such systems would be extraordinarily difficult. Even the Milky Way's known dwarf galaxies are faint and hard to detect, discovered only after years of careful sky surveys and deep imaging. A sub-satellite galaxy would be even dimmer, perhaps made of only a handful of stars, so few that we might only detect the very nearest ones. It is even possible that some of these small dark matter halos exist without making any visible stars at all, leaving them effectively invisible. Yet, if astronomers were to discover even one clear example of such a system, it would be powerful evidence that our understanding of how cosmic structures form, layer by layer, from the largest to the smallest, is indeed correct. There are already hints that this might be true. The Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, two relatively large dwarf galaxies near the Milky Way, show signs that they may once have had smaller companions of their own. A few tiny faint objects found nearby could actually be their satellites, not satellites of the Milky Way itself. If that is confirmed, then we already have proof of sub-galaxies right here on our cosmic doorstep. This also suggests that some of the stars and gas being pulled from the Magellanic Clouds into long tidal streams may not have originally belonged to them at all. They could have come from even smaller galaxies that were caught in their gravitational grasp. And so the question remains, could a small, faint galaxy like Draco, already struggling to survive within the Milky Way's powerful tides, still have its own even tinier companions clinging to it? According to theory, models of dark matter tell us that every halo of dark matter, no matter how tiny, should contain even smaller pieces inside it. But in reality, the smaller and weaker a galaxy is, the harder it becomes for it to keep hold of those tiny companions. The immense gravitational pull of the Milky Way tends to steal them away. For a smaller satellite galaxy to keep its own miniature satellites, those companions would have to orbit extremely close to their parent, almost hugging its centre. They would circle it the way a moon orbits a planet, staying tightly bound so they would not be torn apart by the Milky Way's greater force. If such miniature galaxies existed, their faint light would almost blend into the glow of their parent stars, making them incredibly difficult to spot. These ultra-faint companions would be among the dimmest and most delicate systems in the universe. Perhaps only a few hundred stars held together, not by their own gravity, but by the invisible dark matter halo that surrounds them. Detecting such faint neighbours would require more than just pictures. Astronomers would need to measure how the stars move. By tracking groups of stars that drift together through space, researchers could uncover hidden clumps that reveal the presence of these mysterious companions. In the future, data similar to that from the European Space Agency's Gaia mission might show whether dwarf galaxies, such as Fornax, are home to these tiny star clusters moving in strange, synchronized ways, evidence of an unseen connection beneath the surface. But if such sub-galaxies exist, another question arises. Do they form stars at all, or are they so small and fragile that their gas is stripped away before star formation can even begin? Many of them might be completely dark, tiny halos of invisible matter without a single shining star, detectable only through the way they tug on nearby stars or subtly twist the patterns of tidal streams that flow around their parent galaxy. Long ago, astronomers wondered whether systems within systems might exist even closer to home. Planets had moons, but could moons themselves have smaller moons? Eventually we learned that yes, a few moons do have their own tiny companions, though these are usually small captured fragments that do not last long. Now that same curiosity stretches to the scale of galaxies. Could there be a hierarchy of systems that never ends? Does the cosmic chain stop at dwarf galaxies, or is there one more step, a galaxy orbiting a galaxy that orbits another galaxy? If sub-galaxies are ever confirmed, it would reshape our understanding of the Milky Way's vast family. No longer would we picture a simple structure of large galaxies surrounded by smaller ones. Instead, the story would grow more intricate, a cosmic family tree full of branching layers, where even modest dwarf galaxies have their own tiny companions. This would make the study of galactic archaeology richer and more complex. scientists would have to trace not only how the Milky Way swallowed its smaller neighbours, but also how those smaller galaxies devoured their own satellites before being captured themselves. Every piece of evidence, the chemical makeup of stars, the paths of stellar streams, and the shapes of tidal debris would need to be re-examined with this new, layered picture in mind. Though this idea remains speculative, it fits beautifully within the larger pattern of the universe, which seems to be built like a set of cosmic nesting dolls. Galaxies are born inside dark matter halos, which themselves sit within even greater halos, forming structures that repeat from the smallest scales to the largest. Gravity, it seems, loves to build hierarchies. Whether there is a final step, whether the ladder of satellites stops here or continues downward one more level, remains an open question. Perhaps in the coming decades, as technology grows and our ability to detect faint motions improves, the universe will finally reveal just how deep this cosmic nesting truly goes. In our local cosmic neighbourhood, known as the Local Group, two great spiral galaxies dominate the scene like celestial rulers, the Milky Way and the Andromeda Galaxy. They are often seen as twin giants, each surrounded by a crowd of much smaller companion galaxies. Both swirl gracefully through space, wrapped in spirals of stars, gas and dust. Yet, their peaceful appearance hides a slow and inevitable fate. They are on a long journey toward one another, set to collide and merge in several billion years. At first glance, the two galaxies might seem almost equal in size and power, but when scientists look more closely at their surrounding satellite systems, the balance begins to tilt. Andromeda appears to have more companions, more variety among them, and in some ways, a richer and more complex collection that challenges our ideas about what a galaxy family should look like. Comparing these two great systems side by side gives astronomers a rare chance to test theories about how galaxies form, how the cosmic environment shapes them, and how dark matter influences the smaller structures that orbit within their vast halos. One of the clearest differences between the Milky Way and Andromeda lies in simple numbers. The Milky Way currently has about 60 known dwarf satellite galaxies, although new discoveries are still being made as telescopes and surveys become more advanced. Many of these companions are so faint that they are almost invisible, barely distinguishable from the background of stars. Andromeda, however, seems to host at least 90 confirmed satellites, and possibly even more, depending on how deep our observations go. Part of this difference can be explained by our point of view. Because we live inside the Milky Way, it is difficult to see its faint companions clearly. Many of them hide behind thick fields of stars, dust and gas near the galactic disk. Observing Andromeda, on the other hand, is like looking at another galaxy from the outside. Its satellites can be seen more easily, spread around it like distant fireflies circling a glowing lantern. Still, even after accounting for these observational challenges, Andromeda truly seems to have more companions than the Milky Way. Why might this be so? Did Andromeda simply form in a way that allowed it to capture or hold on to more small galaxies? Or has the Milky Way lost some of its former satellites over time, stripped away by powerful gravitational tides, or absorbed in past galactic mergers? The differences do not end with the numbers. The types of satellites surrounding each galaxy also tell different stories. The Milky Way's companions are mostly very faint and ancient dwarfs, such as Draco and Ursa Minor, which are small, gas-poor spheroidal systems where star formation stopped long ago. In contrast, Andromeda's entourage includes several brighter and more active satellites, such as M32 and M110. M32, for example, is thought to be the core of a once much larger galaxy, whose outer layers were torn away by Andromeda's powerful gravity, a dramatic reminder of the violence that shapes galaxies. M110, another of Andromeda's bright companions, shows signs of having gone through several bursts of star formation, perhaps triggered by tidal encounters with its massive parent galaxy. Even Andromeda's smaller dwarfs have distinct chemical signatures, suggesting that they evolved differently from those orbiting the Milky Way, possibly due to variations in how their stars formed and enriched their surroundings over time. One of the most surprising discoveries about Andromeda's satellites is that many of them seem to lie in a single, enormous and thin plane, almost like a vast invisible disk of dwarf galaxies moving together through space. This arrangement is highly unusual, since computer simulations of dark matter predict that satellites should be scattered more randomly, forming roughly spherical halos rather than organized planes. Some researchers believe this pattern could be a coincidence, but the alignment is too striking to ignore completely. By comparison, the Milky Way's satellites are more loosely distributed, though even here, hints of similar but less pronounced alignments have been found. If Andromeda's Great Plane is real, it might mean that many of its satellites fell in together as part of a larger group, instead of arriving one by one over time. Another key difference lies in the life stories of the satellites themselves. Most of the Milky Way's dwarfs stopped forming new stars billions of years ago, leaving behind only ancient dim populations, fossil remnants of an earlier cosmic era. In contrast, several of Andromeda's satellites show evidence that star formation continued for longer, or even restarted after long pauses. This suggests that Andromeda may have influenced its companions in more complex ways, perhaps through stronger tidal interactions or more frequent mergers that stirred up gas and reignited starbirth. Understanding why Andromeda's dwarfs are more chemically varied and historically active could reveal why two galaxies that seem so similar on the surface ended up with such different families of satellites. Brightness also plays a major role in what we can detect. Some of the Milky Way's ultra-faint dwarfs contain only a few thousand stars, so dim that they are barely detectable even nearby. Andromeda, which lies about 2.5 million light-years away, certainly has its own faint satellites, but they are far harder to find at that distance. Current surveys are only just beginning to reach the limits where such tiny galaxies could be seen. Future telescopes may reveal more of them, helping to balance the count between the two great spirals. But if they do not, and Andromeda truly has fewer ultra-faint satellites, it could mean that deep physical differences exist between the two systems, perhaps in the way dark matter halos give rise to visible stars. Finally, the Milky Way has something that Andromeda seems to lack: two large and bright irregular companions, the large and small Magellanic Clouds. These galaxies are massive enough to have their own possible satellites and are currently interacting with the Milky Way, creating a long stream of gas called the Magellanic Stream. Andromeda has no direct equivalent to this lively pair, though M32's past, as a galaxy stripped and reshaped by Andromeda's gravity, may represent a similar story told in a different way. From a theoretical point of view, comparing the Milky Way with the Andromeda Galaxy is one of the most valuable things astronomers can do. These two vast spiral galaxies are like cosmic twins. They are roughly the same in mass and age, both shining as mighty rulers within our local group. Yet, despite their similarities, their families of smaller companion galaxies are surprisingly different. This makes them a perfect natural experiment for scientists who want to understand how galaxies grow and evolve. By studying the Milky Way and Andromeda side by side, astronomers can test whether the differences they see are caused by the way we observe them, by their surrounding environments, or by something deeper in the laws of physics themselves. If Andromeda's unusual alignment of satellite galaxies turns out to be a common pattern across the universe, then scientists may have to rethink parts of our grand cosmological models. But if the Milky Way's satellites are dimmer, smaller, and more quenched, meaning they no longer form many new stars, it could mean that something special or even hostile is happening within the invisible halo of dark matter that surrounds our own galaxy. Every difference between these two spirals becomes a test, a chance to push the boundaries of what our theories can explain. In many ways, the Milky Way and Andromeda are like siblings who share the same family background, but grew up with different experiences. One might have had more peaceful times, while the other faced more violent cosmic encounters, shaped by collisions, tidal forces, and the neighbourhoods they live in. The local group, our small corner of the cosmos, stands in a perfect middle ground. It is not as crowded as the giant galaxy clusters where galaxies collide too often to keep clear records of their long, slow histories. Nor is it as empty as the vast cosmic voids where galaxies drift so far apart that interactions become rare and faint. Instead, it is a loose family of three main galaxies: the Milky Way, the grand spiral that holds our Sun; Andromeda, its larger and more distant twin; and Triangulum, the smallest but still mighty third member, all surrounded by more than 80 tiny dwarf galaxies of many different shapes, sizes, and brightness. This mix of giants and dwarves makes the local group a miniature version of the wider universe, a smaller, more detailed stage where astronomers can study the drama of galaxy evolution up close. Because these galaxies lie within a few million light-years, telescopes can actually resolve their stars and trace their structures in ways impossible for galaxies farther away. To scientists, the local group serves as a cosmic laboratory, a nearby testing ground where theories about galaxy birth, growth and interaction can be directly checked against real evidence. By comparing how dwarf galaxies orbit the Milky Way with how they move around Andromeda, and by examining how Triangulum interacts with both, astronomers can build a fuller picture of the invisible forces shaping galactic life. Each dwarf galaxy tells part of the story. Some still carry the scars of past collisions, others preserve the chemical fingerprints of ancient starbursts, and many bear the marks of their surroundings, proof that even the tiniest systems have rich and varied histories. Although Triangulum is often overshadowed by its larger neighbours, it plays an important part in this grand experiment. As the third great spiral galaxy in the local group, it is smaller and less massive than either the Milky Way or Andromeda, but it still hosts its own family of faint companions. These satellites are harder to study because Triangulum lies farther away, yet they provide a crucial third point of comparison. If the Milky Way's dwarfs differ from those around Andromeda, Triangulum helps decide whether those differences come from environment, history, or random chance. For instance, if both Andromeda and Triangulum have satellites that are stretched or elongated while the Milky Ways are more compact, that hints at deeper patterns in how galaxies evolve, rather than simple coincidence. The local group also allows scientists to explore how small galaxies interact with one another before being drawn into the gravity of the giants. Sometimes two dwarves orbiting close together form temporary pairs, their mutual gravity tugging at each other's stars long before the pull of the Milky Way or Andromeda takes control. Evidence suggests that some of the Milky Way's current satellites once entered as bound groups, little families of galaxies already linked by gravity. The same may be true for Andromeda. These small associations are like miniature versions of the local group itself, showing how cosmic structure grows step by step, from small groups merging into larger ones. By mapping the positions and motions of these dwarfs, astronomers can reconstruct their journeys, discovering which arrived alone and which fell in together. Some dwarf galaxies are extremely primitive, with chemical compositions that have barely changed since the universe's youth. Others are more chemically enriched, revealing long histories of star birth and death. Comparing these differences helps scientists understand whether the massive galaxies shape their satellites' chemical lives, or whether the dwarfs largely developed on their own before capture. Dark matter studies also gain enormous insight from this neighbourhood. Because astronomers can measure the movements of stars within nearby dwarfs so precisely, the local group provides some of the best evidence about how dark matter is distributed on small scales. With three main galaxies, the Milky Way, Andromeda, and Triangulum, each surrounded by its own satellites, researchers can ask whether certain dark matter puzzles, such as the core versus cusp problem, appear everywhere or only in particular settings. The local group is not frozen in time. The Milky Way and Andromeda are slowly moving toward each other and will collide in several billion years, with Triangulum likely drawn into the encounter. When that happens, many of their dwarfs will be stripped, merged, or scattered. Some of the faintest satellites may dissolve completely, their stars spreading out to form glowing halos around the giants. Others may survive the chaos but be thrown into new, unpredictable orbits. Studying the local group today gives us not only a snapshot of present-day conditions, but also a preview of how galaxies evolve on larger scales throughout the universe. Because these galaxies are so close, astronomers can do something remarkable. They can study individual stars within many of the dwarfs, rather than seeing them as faint blurs. This allows much more accurate distance measurements, helps identify variable stars that serve as cosmic yardsticks, and even reveals when different generations of stars formed. Such precision is impossible for dwarfs in distant clusters, where their light blends into a faint haze. In this way, the local group acts as the universe's ground truth, the standard by which astronomers test their models and theories before applying them to galaxies farther away. It may be small compared to the immense galaxy clusters that fill the cosmos, but within its modest boundaries lies a universe of lessons. When scientists study it as a whole, seeing not just the Milky Way but also Andromeda, Triangulum, and the dozens of dwarfs that orbit them, they uncover the delicate and beautiful dance of gravity, time, and matter that shapes the very structure of the universe itself. When we look far into the future of our Milky Way, one enormous event stands above all others: its eventual and unavoidable collision with the Andromeda Galaxy. This future meeting of two spiral giants will not be a sudden crash, but a slow and graceful dance lasting billions of years, gradually reshaping the sky itself. Stars will drift into new paths, clouds of glowing gas will mix and swirl, and the familiar face of our galaxy will slowly transform into something entirely new. But while this grand meeting between two cosmic titans captures most of our imagination, there are quieter and equally intriguing questions about what will happen to the smaller members of our galactic family, especially the Large Magellanic Cloud and the Small Magellanic Cloud, often called the LMC and the SMC. These two irregular dwarf galaxies orbit the Milky Way like loyal but restless companions, each with its own motion, gas clouds, and gravitational pull. So what fate awaits them when their parent galaxy finally meets Andromeda head-on? Astronomers have long suspected that the LMC is not just a small side character in this story. It is surprisingly massive. Massive enough, in fact, to tug at the Milky Way's dark matter halo and slightly alter the balance of our galaxy's motion. This means that when Andromeda finally approaches, the Magellanic Clouds will not simply be swept along as helpless bystanders. They will play active roles, their gravity and gas adding new complexity to an already dramatic encounter. Their destinies are deeply tied not only to the Milky Way's future, but also to the precise timing of when the galaxies meet. Computer simulations suggest that the Milky Way and Andromeda will have their first close encounter roughly 4 billion years from now, with their complete merger taking place a few billion years later. By that distant time, the Magellanic Clouds may look very different from the bright, irregular galaxies we see today. Even now, the Milky Way's powerful gravity is slowly stripping them of gas, while tidal forces stretch and distort their shapes. Some models predict that within a few billion years, much of their star-forming material will be gone, leaving only faint, aging remnants of what were once lively star-filled galaxies. If that happens, they will drift into the Andromeda collision as pale ghosts, dim witnesses to a much greater transformation. Yet there is another possible future. The LMC's great mass might make it impossible for it to remain a mere satellite forever. Its orbit is gradually decaying, and many astronomers believe that in about 2 to 3 billion years, long before Andromeda even arrives, the LMC could spiral inward and merge directly with the Milky Way. If this happens, the entire story changes. The LMC's stars and gas would become part of the Milky Way's structure, enriching its spiral arms and halo with fresh material. In other words, our galaxy would enter its grand collision already swollen and energized from a smaller merger that came before. The SMC, being less massive, might follow the LMC in its descent, drawn in by its companion's gravity and eventually merging with the Milky Way as well. If this sequence unfolds, the Magellanic Clouds as separate galaxies would vanish before the great Milky Way-Andromeda union ever begins. But if they somehow manage to survive as distinct systems until that time, the combined gravitational forces of the two giants could fling them into unpredictable new orbits. They might be tossed into wide, eccentric loops or even ejected completely, hurled into the vast emptiness of intergalactic space. In some simulations of galaxy mergers, smaller satellites are not quietly absorbed. They are catapulted away, victims of the ever-shifting balance of cosmic gravity. It is even possible that the Magellanic Clouds could be thrown out of both galaxies entirely, drifting freely across the local group as lonely, wandering dwarfs. Another possibility is that the LMC or SMC might be captured by Andromeda instead of the Milky Way. When galaxies merge, their stars, gas and dark matter mix chaotically, and the fates of smaller companions can change depending on how the gravitational tides unfold. The LMC, for instance, could end up orbiting the merged remnant of the Milky Way and Andromeda, a future super-galaxy that astronomers sometimes call Milkomeda. If that happens, the Magellanic Clouds would live on, but as fragments within a much larger and grander system, their independent identities forever absorbed into a new cosmic whole. Despite how violent it may sound, a galaxy collision is not like two cars smashing together. Stars are so far apart that almost none will physically collide. Instead, it is gravity that performs the real drama, reshaping orbits, compressing gas, and triggering waves of new star formation. When vast amounts of gas are funneled into galactic centers during these mergers, they ignite starbursts, brief but spectacular episodes where thousands of new stars are born in brilliant flashes. The LMC and SMC both contain rich stores of gas, and if they still hold on to that gas when the Milky Way and Andromeda finally merge, they could serve as reservoirs feeding those future starbursts, lighting up the skies of the newborn galaxy with breathtaking brilliance. Interestingly, the LMC appears to be wrapped in its own dark matter halo, which makes it sturdier and more resistant to being torn apart. If this dark halo is as massive as some studies suggest, it could allow the LMC to survive much longer than other dwarf galaxies during the merger. While many smaller companions may be shredded into streams and trails of stars, the LMC might endure as a distinct core, a fossil of its former self buried within the heart of the future Milky Way galaxy. Billions of years from now, if intelligent beings still gaze at the night sky from what remains of Earth, or from somewhere else within that future galaxy, they might see a breathtaking scene of starlight, with entire constellations made of stars that once belonged to the Milky Way, Andromeda, and the Magellanic Clouds. Though we cannot say for certain how this story will end, the idea that these small, restless galaxies could play such important roles in shaping the universe's grand future makes their journey all the more fascinating and beautiful. When the Milky Way and Andromeda finally meet, countless stars will be swept into new patterns and cosmic dances. Among them will be the faint but beautiful legacies of the large and small Magellanic Clouds, two dwarf galaxies that have long orbited our own. But this raises a fascinating question. Can small galaxies ever escape the grip of their mighty masters? At first glance, it seems impossible. The relationship between a massive galaxy and its tiny companions often appears one-sided. The giant's gravity pulls the dwarfs inward, stripping away their stars and gas until, in time, it absorbs them completely. Yet the universe rarely follows simple rules. Gravity, though powerful, is also a living force. It changes as galaxies move, collide, and evolve. Because of this, not every satellite is doomed to fall. Some may find ways to break free, turning into wanderers of the cosmos. To understand how a dwarf might escape, one must first grasp the idea of escape velocity. Every massive object, a planet, a star, or a galaxy, has an invisible limit defined by how fast something must move to break away from its pull. For Earth, rockets must reach a speed of about 11 kilometers per second to escape. Near the Sun's location in the Milky Way, the required speed is roughly 550 kilometers per second. Most dwarf galaxies move far more slowly than that, safely bound in their orbits. Yet, under special conditions, something can give them an extra push. That something often comes from interaction. When two large galaxies approach or merge, their gravitational fields twist and overlap, creating chaos. In this storm of forces, smaller satellites can be flung outward, gaining enormous speed. Some are drawn deeper into the merging system, but others are hurled into the dark between galaxies, stripped not by destruction, but by motion itself. Computer simulations have shown these miniature galaxies being tossed into intergalactic space, where they drift freely like cosmic exiles, rogue dwarfs no longer tied to any master. There is also a more elegant route to freedom, the gravitational slingshot. Just as spacecraft use a planet's gravity to gain speed during flybys, a dwarf galaxy passing close to a massive companion can receive a boost. If the angles line up just right, this assist adds to its energy instead of slowing it down. Instead of spiraling inward, the dwarf accelerates, moving onto a wider and more stretched orbit. In extremely rare cases, that path may carry it beyond its galaxy's reach entirely. This idea isn't just theory. Astronomers have actually observed similar effects. In some pairs of small galaxies, one falls into a giant's orbit while the other speeds away at astonishing velocity. In certain regions of the nearby universe, researchers have even found dwarfs moving too fast to remain bound to their supposed hosts. Some seem to be escaping whole clusters of galaxies, environments far denser and more turbulent than the Milky Way's halo. If dwarfs can be ejected from such crowded regions, then they can likely be thrown out from individual galaxies as well. For decades, scientists have debated whether the large and small Magellanic Clouds are true long-term satellites of the Milky Way, or just recent visitors passing by. Precise measurements from the Hubble Space Telescope revealed that they are moving faster than expected if they were deeply bound. Some models suggest that depending on how their orbits evolve and how friction with the Milky Way's dark halo slows them down, they might one day escape our galaxy's grasp entirely. If they stay, they will eventually merge with the Milky Way. If they escape, they could become solitary wanderers drifting through space, perhaps to be captured by Andromeda, or to travel endlessly into the cosmic void. A dwarf's ability to flee depends strongly on the true size and mass of the Milky Way's dark matter halo, the vast invisible cocoon surrounding it. If the halo is larger than we think, escape is nearly impossible. If it is smaller, freedom becomes far more likely. Since astronomers still do not know the halo's exact shape or reach, the fate of these dwarfs remains an open question. Even if a dwarf galaxy itself cannot escape, parts of it often can. Streams of stars pulled away by gravity can stretch across the Milky Way's halo, surviving for billions of years. Some of these stellar trails may even drift beyond the halo's boundary, becoming faint intergalactic ribbons, the ghostly remains of once-living galaxies. In the early universe, when galaxies were smaller and closer together, encounters were far more frequent. Dwarfs may have been tossed around constantly, switching from one master to another or being flung free into space. Some of today's lonely dwarf galaxies may be survivors of those ancient expulsions, quiet travellers carrying no memory of their origins, shining faintly in the darkness between giants. This possibility excites astronomers. If too many isolated dwarves exist to be explained by normal formation theories, perhaps many are not original independents at all, but escapees, relics of past collisions and gravitational battles. And even if they flee from the Milky Way or Andromeda, they are not truly lost. They may still drift within the broader gravitational field of the local group, the vast family of galaxies that includes the Milky Way, Andromeda, and Triangulum. In that sense, escape is relative. A dwarf may leave one master's halo, only to remain bound to the greater community of the local group, wandering for billions of years, waiting for a new encounter, or perhaps a new home among the stars. In the decades to come, tiny dwarf galaxies may step out of the shadows of astronomy and take centre stage in our understanding of the cosmos. For much of the last century, these small galaxies were treated like curiosities, too faint, too fragile, and too inconspicuous to play any major role in the grand cosmic story. They were considered side characters in a drama dominated by giant galaxies like the Milky Way or Andromeda. Yet, time and again, dwarfs have surprised astronomers, proving themselves to be crucial pieces in the puzzle of how galaxies form, grow, and interact. The main challenge has always been finding them. They are elusive because they are small, dim, and often easily lost against the backdrop of the starry sky. But a new era is dawning. With next-generation telescopes coming online, the shadows that hide these cosmic minnows are finally being pulled back. Soon, scientists hope to discover not just dozens, but possibly thousands of new dwarf galaxies. Each one could carry vital clues about the hidden history of our universe, whispering secrets from its earliest chapters. The first major leap will come from the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope. This extraordinary facility will scan the entire visible sky of the southern hemisphere with a depth never before achieved. Unlike previous surveys that only looked at selected regions, Rubin will repeatedly sweep the whole sky over the course of a decade, creating what could almost be called a living movie of the cosmos. For dwarf galaxies, this is nothing short of a treasure trove. Many of the faintest dwarfs have remained hidden, not because they are distant, but because their faint light blends into the background. Their stars are too few to stand out individually, and their combined glow barely rises above the darkness of the night. But by collecting images over many years, Rubin will be able to tease these faint signals out of the cosmic noise. Areas of the sky that now appear empty may suddenly reveal countless hidden structures. Astronomers hope Rubin will uncover the faintest galaxies in the local group, possibly reaching the very limits of what we can define as a galaxy. If Rubin finds large numbers of these ultra-faint dwarfs, it could confirm our current models of galaxy formation. If not, the universe may be telling us something even deeper. Rubin will not work alone. NASA's Nancy Grace Roman Space Telescope will play a key supporting role. While Rubin looks from the ground, Roman will operate from space, offering crystal-clear images unaffected by Earth's atmosphere. Its wide-field camera is capable of capturing enormous swathes of the sky at a resolution comparable to the Hubble Space Telescope. Roman will confirm dwarf galaxy candidates found by Rubin and reveal their internal structures in stunning detail. Faint streams of stars, central clusters, or evidence of recent interactions with larger galaxies. Roman will also peer farther beyond our local group, spotting dwarfs orbiting galaxies tens of millions of light-years away. This will help astronomers see whether the patterns we observe locally hold true across the broader universe. Together, Rubin and Roman form a powerful two-part system, one scanning broadly and deeply from Earth, the other zooming in with clarity from space. And then there is the James Webb Space Telescope, already in operation, which adds an entirely new dimension. Webb, though not designed for wide surveys, can explore the inner lives of dwarf galaxies with infrared sensitivity, peering through dust and detecting the faint glow of ancient stars. It has already glimpsed distant, tiny galaxies that resemble the first dwarfs, giving us a rare look at the universe's original building blocks. In the future, Webb could study nearby ultra-faint dwarfs in exquisite detail, uncovering the ages, compositions, and histories of their stars. Beyond these flagship observatories, many other projects will play vital roles. Radio arrays like the Square Kilometre Array will map the hydrogen gas within dwarfs, revealing how much material they still have for forming new stars and how larger galaxies can strip that gas away. Extremely large telescopes on the ground, with mirrors over 30 meters wide, will resolve individual stars in distant dwarfs, transforming faint smudges of light into detailed stellar systems. Even high-energy observatories will contribute, studying how supernova explosions and black holes within dwarfs affect their structure and survival. Perhaps the most exciting possibility is that Rubin and Roman will uncover entirely new types of dwarf galaxies we never knew existed. There may be ultra-diffuse galaxies, where stars are spread across enormous areas, only revealing their presence when careful surveys detect the underlying dark matter halos. Some dwarfs might be rich in gas but hidden behind clouds of dust, while others may be relic galaxies that never grew beyond their initial burst of star formation. Next-generation telescopes will also allow astronomers to study how dwarfs move. By tracking the motions of their stars, scientists can measure how much dark matter is inside and how it is distributed. These observations may even reveal whether the tiniest dwarfs are still forming new stars today, or if star formation ceased billions of years ago. Active dwarfs could challenge our understanding of how galaxies control their own growth, while universally quiescent dwarfs could show the minimum threshold below which star formation cannot continue. Understanding this threshold is crucial to refining models of galaxy evolution and death. If dwarfs helped reionize the early universe, as many astronomers suspect, then mapping their modern descendants is like reconstructing the family tree of the cosmos. Each faint smudge in the sky is a survivor, carrying memories of an age when galaxies were newborn, and studying them in large numbers may reveal how the first light spread across the dark universe. The future promises abundance. Instead of struggling to find a few faint dwarfs, astronomers may soon have more than they can easily catalogue. The challenge will shift from discovery to interpretation, how to weave thousands of small galaxies into a coherent story of cosmic evolution. But this is a challenge astronomers are eager to embrace, because each faint galaxy carries a secret about where we came from and where we're going. And perhaps, in studying these humble dwarfs, we may even question what makes a galaxy truly life-friendly. When most people think of galaxies that might host life, their minds naturally drift to the grand and majestic. They picture enormous spiral galaxies with their sweeping arms of stars, or massive elliptical galaxies where billions upon billions of suns glow in a quiet, stately dance. These giants feel like the obvious candidates for complex chemistry, planets, and perhaps even civilizations. Their sheer size brings both variety and stability. Across their immense disks or rounded shapes, countless star systems coexist, some tumultuous, some serene, while clouds of gas and dust swirl, collide, and recycle endlessly, forging new generations of stars and planets. But dwarf galaxies tell a very different story. These small, fragile structures are often shaped and moulded by the gravitational whims of their larger neighbours. They host far fewer stars, have less shielding against harmful radiation, and endure far more chaotic histories. Life, if it exists, would face challenges in every corner of these miniature cosmic realms. The first obstacle is the sheer numbers. A galaxy like the Milky Way contains several 100 billion stars, offering innumerable chances for Earth-like planets to form in stable orbits. A dwarf galaxy, by contrast, may have only a few million, or even just a few 100,000 stars. That immediately reduces the odds of having multiple Sun-like stars with the stability needed for life to develop. Ultra-faint dwarf galaxies often contain nothing but ancient, dim stars, relics from the earliest epochs of the cosmos. With so few potential homes, the chances for life may seem vanishingly small, yet small odds are not the same as impossibility. Even a single star system with the right chemistry could spark life. Life, as we know it, depends on a delicate mix of elements. Carbon builds complex molecules, Oxygen fuels water and respiration, nitrogen and phosphorus drive biochemistry, and iron and magnesium shape planetary cores and biological processes. In large galaxies like the Milky Way, these elements accumulate over billions of years through stellar recycling. Massive stars explode as supernovae, scattering heavy elements across space. These materials then seed new stars and planets, enriching each generation. Dwarf galaxies, however, struggle to hold on to such treasures. Their shallow gravitational pull allows much of the material from stellar explosions to escape into intergalactic space. Many dwarfs remain chemically primitive, trapped in a kind of cosmic adolescence, with stars that carry only trace amounts of heavy elements. This makes planet formation more difficult. Without enough heavy elements, rocky planets, those essential cradles for life, may be rare or absent. Gas giants could still form, but planets with stable surfaces, atmospheres and oceans would be far less common. Yet there is hope in the middle-sized dwarfs. Observations show that some still experience chemical enrichment. Planetary nebulae, star clusters, and stars with higher metal content suggest that the building blocks for rocky planets can exist in these galaxies. Dwarf galaxies also face relentless exposure to cosmic hazards. Lacking thick layers of gas and dust, their stars are more vulnerable to intergalactic radiation and the energetic winds of massive short-lived stars. Ultraviolet radiation can strip atmospheres from nearby planets, making the maintenance of liquid water or protective envelopes extremely challenging. Life, if it exists, might need to hide underground, underwater, or in other sheltered niches. Even so, dwarf galaxies may harbour hidden safe zones. Just as deserts on Earth do not prevent life from flourishing in caves or shaded oases, small pockets of stability could exist among the stars. Long-lived, low-mass stars such as red dwarfs could provide steady energy for trillions of years, far exceeding the lifetimes of sun-like stars. Around such stars, even in chemically limited galaxies, the conditions for life might slowly take shape. Many dwarfs orbit larger galaxies, where they experience tidal forces that strip away gas. This can halt new star formation and reduce chaos. Once the disruptive, massive stars fade, the remaining stars burn quietly for billions of years. In this calm, frozen state, planetary systems could enjoy vast epochs of stability. The galaxy may appear lifeless on a grand scale, yet on the level of individual planets, life might have more than enough time to develop. Ultra-faint dwarfs preserve chemical histories from the universe's first billion years. Any rocky planets in such galaxies would be unimaginably ancient, older than Earth by billions of years. Life in these ancient corners could be older than we can imagine. This raises a tantalizing possibility. Perhaps the first stirrings of life in the universe did not occur in majestic spirals like the Milky Way, but in these forgotten, fragile corners of space. However, dwarfs are delicate and highly vulnerable to catastrophe. A single gamma-ray burst, a cluster of supernovae, or even a collision with another dwarf could sterilize much of their limited star systems. Unlike a giant galaxy, which can absorb such shocks without widespread destruction, a dwarf could lose entire regions of habitability in one event. The margin for survival is slim. Over cosmic time, many dwarf galaxies may be torn apart. Their stars scatter into the halos of larger galaxies, and their gas is absorbed into new star-forming regions. Life within these dwarfs might seem doomed, yet even in destruction, hope persists. Planets may travel with their stars into the halo of a larger galaxy, carrying with them the remnants of a once stable, life-friendly environment.